Good morning. Hope you all had a good time coming to New Orleans. Welcome to our CVPR workshop on fair, data efficient, trusted computer vision. This is the third one in the series. This has come about combining in previous years before the third one. We had separate workshops on fairness and data efficiency and trusted computer vision. We thought they all should be together to make sense. I think it makes more sense to be combining all of them. So we combined all of them, and this is the third edition of the combined version. So my name is Nalini Raj, and I'm from University of Buffalo, SUNY, and I'm one of the organizers of the workshop. Sorry, I guess you're having a little. Okay, so as I said, I'm one of the organizers, and there are 7 more of us. We put together this workshop, and probably you might have heard from one of us at different times. So this is our organizing team that we come from industry, academia, and so we have common interest in making AI systems trustworthy, efficient, and fair. That's basically our common goal, and we are looking forward to giving you what we put together. But before that, as probably some of you know who are in the US, that yesterday was the Juneteenth, which is a US holiday now. It happened to be on a Sunday yesterday. It's about commemorating the end of slavery in the US. And this was particularly New Orleans and Louisiana plays a significant role in this. So we encourage all of you to learn more about it. CVPR itself has put up a web page, and you can see the link. Please do visit that. And yesterday, I believe there was some celebration locally as well in New Orleans. So there are probably a lot more going on. Please do look at some of these great commemorating events that have been going around. So our whole day, we have a very packed day. We have several keynote speakers, and then we have papers also. And this it being a hybrid workshop, which you can expect it to have a lot of online presence. We have a lot of people in the Zoom call, and as well as we have people who are the speakers who may be remote, who may be in the room. So we have a mix of all kinds of modes today, but do engage with the speakers, and there will be, some of them will be available online, and we look forward you to enjoy the whole day. Just in terms of logistics, as I said, some speakers are in person, some are remote, but the posters allocated to our workshop are 70 to 84 pages. So you can hang around there for networking or show your work there as well. And we will have, for some of the sessions, live Q&A, or at the end, we will announce that as we go around. Please note the break, particularly the lunch. 12 to 1:30 is the lunch time, and 10:15 to 10:45 in the morning, and 10 to 15:30 for the coffee break. So with that, I guess I will hand over to Mayank, who is going to introduce our first speaker, Anna Ross. Mayank.
Thank you, Dr. Radha. Let me take the privilege to introduce our first keynote speaker, Ms. Anna Roy. She's the senior advisor at NITI Aayog. And Ms. Roy is a 92 batch officer of Indian Economic Services. She has received her education from Delhi University and Delhi School of Economics. Before joining IES, she was a lecturer in Delhi University, and then she moved to the Niti Aayog government agency, and as well as she has worked in different ministries like Ministry of Finance, Ministry of Civil Aviation, and currently in Niti Aayog. She has championed multiple initiatives, and I have worked with Ms. Roy closely on a couple of initiatives, but her portfolio is very rich in terms of the kind of initiatives she has taken at a national level, including the artificial intelligence initiative, the blockchain, the India strategy for blockchain, the approach paper on Aravat, the responsible AI document, which was released in two parts in the last few months, and data empowerment and protection architecture is one of her flagship programs. She has also championed women entrepreneurship platform. It's a Niti Aayog's flagship program, and those who do not know, Niti Aayog is the think tank of Indian by the Indian government, where the futuristic programs are envisioned and executed, and she has championed several of those programs, including the recent National Data Analytics portal also. So we are really honored that Ms. Roy accepted our invitation, and over to Ms. Roy. Ms. Roy, over to you.
Thank you, Mayank, and I would like to thank the organizers for giving me this opportunity to share our views. So two things are clear from my introduction. First of all, I work in a think tank of Government of India, and second, I am not a technology person. I am an economist by training and public policy proponent, and I bring in that aspect to the entire work which I do in Niti Aayog around technology, emerging technology and data, and hopefully pick up something while I'm working on it. So today I will be giving you just a brief peek into how we are approaching the entire issue of responsible use of this technology from the public policy perspective. I'll start with 2018, the year when we released the National Strategy for Artificial Intelligence. And the strategy is there on the website. It is widely referred to. One of the things that the strategy advocated was responsible use of AI to address ethical and various other considerations. The strategy did not go deep into this area, but it was like watch this space kind of a thing, following which we worked with various stakeholders. And in July 2020, we came up with the first part of towards responsible AI for all. Now, the national strategy on AI was called AI for All, which takes after the basic premise of the policy which the current government has of inclusive growth. That is why we called it AI for All. And the first paper on responsible AI spoke about the principles which should be followed for achieving the goal of AI for all. Following which we have been releasing various other documents on responsible AI. As we go along, I will just briefly refer to it. Now, when we brought out the national strategy document, the landscape, what we encountered was the tremendous economic and social potential that the technology had for a country like India, which for ages has been struggling with access barriers, lack of resources in key sectors like health, education. So there were several studies which indicated significant economic potential of AI. We had also a landscape where social sectors were lagging in terms of investment in this area. So we had sectors like financial sector, where the investment was more bottom line driven, but sectors like health, education, which were more characterized by public goods, were not getting requisite amount of attention from the private sector. And also the, the scope of India being the research bed for the rest of the world, where we have the resources, we have the challenges, we also have a mandate to promote technology. So the kind of thing where, you come solve for India and you are able to solve for 40% of the world's population, which is facing similar problems. So with this kind of a background, we gave a roadmap for promoting AI in the country. And on the responsible AI ecosystem, we made the statement that unless we address the issues around responsible use of AI, we will not be able to realize the potential. And it is necessary that the AI systems are managed in such a manner that various concerns are identified upfront and are addressed suitably. Globally, adoption of AI was increasing across industries, and if ethical aspects are neglected, then they are bound to have serious social and economic consequences, which for longest period of time could kind of unsettle the adoption of the technology. With that, we started our work on how to bring in the responsible use of a technology which itself was evolving. As at the first instance, we tried to address it through two considerations. One was systems and the other was societal. So in systems, systemic considerations, we looked at the direct impact of the technology, where citizens being subject to a specific AI system can be exposed to it, be it privacy, be it ethical issues, discrimination, lack of clear accountability, etc. The second was more the societal considerations, which had an indirect impact due to overall deployment of AI solutions in society, whether it is impact of work, that is future of work, future of jobs, large scale unemployment leading to adoption of larger technology, the social media menace with deep fakes, and threat to social harmony because of these facts. So on the systems consideration, as I said, the technology itself is still evolving. We still are in a black box phase. There are issues relating to fairness, exclusion, accountability, privacy, security. However, we saw that there are legislative and product development approaches through the adoption of which these risks could be managed. We also examined the global practices around the framework, the sector-specific initiatives, and the legislative route wherever these have been taken, whether it is the Personal Data Protection Act of Singapore or the GDPR or the California Consumer Privacy Act in the USA. Coming to the Indian scenario, we realized that, already we have sector-specific rules, sector-specific policies, legislations in place, which can easily be leveraged to address many of the considerations, the risk. Also, our data protection bill was already on the anvil, though it is still being finalized. And on the overall framework, there was no framework. So Niti Aayog came up with a framework by propagating 7 principles for going forward. Overarching principles, it was felt, would help to guide formation of standards and regulations and a framework which can be used in the times to come. For areas such as privacy, etc., it was felt that the regulations which already exist should be leveraged, and we should not really look for any new regulatory provisions to be in place. The national strategy on AI also spoke about the technical approach. That is how technology itself can be leveraged to overcome many of these problems. And here we recommended active use of this technology by funding research in this area. And it was noticed at that time, and we increasingly see how over time, the ethical AI is attracting a lot of interest, and you have to just look at all the conferences in AI to see that this is one of the most important areas of research today. However, the applications are increasing at such a rapid rate that we need to have a more proactive approach of promoting the technology to address issues of the responsible use of this technology. So I think there we are still lagging, and it needs to be promoted. On the societal consideration, again, as I said, it's the malicious use as well as impact on jobs. And here, we didn't have too much. We had very, very generic kind of recommendation because these are all very evolving things, and the jury is still out on how to deal with them. The principles that we developed, basically 7 principles are around safety, equality, inclusivity, privacy, transparency, accountability, and on protecting and reinforcing positive human values. The changing nature of technology necessitates that regular updates of this. So this is not something which is cast in stone. As technology evolves, as the ground rules change, I think we need to kind of have an open kind of mind how to address them. Following this paper, we came out with a part 2 of the paper, which spoke about the framework for enforcing these principles. Their detailed institutional arrangement and other recommendations were given for public sector, private sector, research institutions in a 3-pronged manner, where on the regulatory aspect, it was felt that we should have a light touch regulation and work through constitution of ethical committees, both at the public sector level as well as in the research institutes, encourage self-regulation in general in the private sector, mandate adherence for high-risk use cases, and incentivize mechanisms to ensure adherence to these principles. The policies which we talked about were around managing and updating principles for responsible AI, promoting research, provide clarity on expectations from AI systems, enable access to responsible AI tools, education and awareness, coordination with various sectoral AI regulators, and represent India and other emerging economies in international AI dialogue on responsible AI, so that the unique position from which countries like India come from can be presented and well appreciated in the global fora. The next thing which we wanted to do was actually, work on use cases and to see how these principles get converted into use cases. So the third part of the paper is under preparation, and in a month's time, we hope to come up with the discussion paper. The first use case which we have taken is on facial recognition technology, which we see is being used by the government in several forms, and not necessarily following a particular, approach of particular framework. And this is where we brought out a pilot project. The first thing which we did was to set up an expert committee and with the experts from legal, technical and policy arena who were part of this committee, who guided the development of standards and specifications and the processes to be followed in one particular pilot project which we were implementing. The project is now closure at the product has been developed, and I think now it would be deployed in a sandbox arrangement. Parallelly, what we have done is to write about the processes, identify the problems that were faced, identify the specific policy and legislative gaps which were noticed, and a mechanism and matrix which should be in place for any of these facial recognition technology projects in public space. So that paper is still under works, and in a month's time we should be in a position to release it. Going forward, we will be exploring more such use cases, and possibly real life use cases, so that we can identify what are the problems on the ground, what are the challenges while implementing these projects, adoption of these technology. So that is what is on the anvil, and it would be great when we bring up this discussion paper to get feedback from the participants and other experts who are part of this dialogue today. And I would request Mayank, who has been part of this exercise, to keep all of you posted through this forum. And we look forward to getting inputs from all of you, because whenever we come up with a policy or a research paper, the first step is to put up a discussion paper for public comment. So that is an opportunity for all, whether you're an expert from policy or technology or legal space, you can comment on it and enrich the work that we are doing. So with that, I will end my intervention right now and hand it over to Mayank. Thank you very much.
Thank you, Mr. Roy. I believe there was, a slight confusion that you were using some slides, and those slides were not visible to the participants. So if you can share your slides, I'll share with the participants later on. So now there is time for question and answer. Is there any question? Dr. Arthur, is there any questions from the audience present over there? Probably you can ask the questions there.
Are there any questions locally here to relate to the speaker? I had a question myself, so I guess you kind of hinted about those 7 principles. Is there a chart or something that you could share with us to describe a little more detail? Because I think they were very pertinent principles that I think all of us should be very much aware of, and we want to make it as our principles of 7 dimensions. So please share that with us.
Certainly, actually, I was reading out from our draft discussion document, which was in the form of a deck, and I'll be happy to share it. Actually, it is there on our website also. So if you go on Niti Aayog website, I can share the link. All these documents are there on the website. We have 8 such publications. And, one publication which I did not refer to is the consent-based data sharing. And in our view, that is the future of responsible, use of this technology, because it allows you to share data seeking the consent of the individual. And iSpirit, which is the think tank, technology think tank in India, they have developed the architecture. So that paper is also there on NITI website. I see Mayank has already shared the link, and all these documents are there. Actually, I was reading out only from this PDF file. I did not, unfortunately, there was some communication gap, and I did not have a prepared presentation. That's why I was not sharing. Thank you. But I will share. He's already shared the documents.
So thank you. No, I think it is very important for us technologists in this room here who are kind of heavily entrenched in developing new versions of vision algorithms. So responsible AI policies are very, very important for us. So I think it would be very useful to go over those documents. Thanks, Mayank, for sharing all of them through the chat here. And are there any questions through Zoom? Other participants, we have around all the participants, you can post your questions on the chat. We will read it out if there are any questions.
So, Mr. Roy, one question. So generally, like creating these rules or the guidelines is one thing, but operationalizing where we have to have a mechanism to enforce these guidelines. So I'm sure the audience would be interested in knowing that what are the mechanisms Indian government is thinking of when how to operationalize these responsible AI paradigms.
So the part 2 of the paper which you have just shared talks about the mechanisms, and the facial recognition technology pilot paper which we are doing that actually talks about a live use case and how some of these principles are being adopted in a particular live project. So I did read out some of the initiatives or some of the ways in which it can be addressed. I think it might have been missed, but I would again request everybody to go through both these documents. It talks about, the part 2 talks about how to enforce these principles. And we feel that a one size fits all is not something which really happens. It has to be a use case driven approach. So facial recognition in a live project is one use case. The second use case, which we are presently actually discussing with our colleagues, is the immersive technology, XR, and what are the challenges there? How can we overcome it? So we are presently following a very use case based approach in identifying, how to adopt many of these principles.
Thank you, Mr. Roy. I really appreciate your time and truly appreciate your willingness to come and share with the international audience. And I'm sure if there are any more questions, I'll be able to pass on those questions to you. Thank you very much.
Thank you very much.
We in particular want to express my thanks to you because of, we are starting the day here. It's almost end of the day there. So thank you for staying for us and making yourself available through a video call. Yes, so then, I think we seem to have lost your audio for some reason.
So I'm saying thank you for having me, and it's an honor to be among such technology gurus in the same conversation, and I feel privileged. Thank you very much.
This is basically the intent of the workshop, is to bring people from different spheres of the world come together. And so thank you for joining us. And the next speaker, Jian, will introduce. And so thank you. Please wait for the next speaker.
Thanks. And so coming up next, we are very happy to have Professor Thomas Brooks to give a keynote. Professor Thomas Brooks is a professor for pattern recognition and image processing, and also the head of the computer vision group at the University of Freiburg in Germany. Professor Brooks, please.
Yeah, thank you. I will share my screen. Can you see it?
Yes.
And now also full screen, right?
That's correct.
Good. Yeah, thank you very much for having me here. I hope my talk can provide a little bit of insights. Some of you may have these insights already. Some of them may not have them already. So I think that's the purpose of my talk. And I want to show you a little bit the way towards open world generalization. So the last few years have served us quite well with deep learning as the key technology, and a whole industry has been built around this. But we probably all admit that what we have achieved is great, but it's quite different from human learning. So we both in the way how we do the learning, but also in the outcome, so in the quality of what we have learned. And one thing that we can see that doesn't work so well as with humans is the generalization to out of distribution data, which is particularly problematic then also in many applications. For example, when people train their algorithms on US roads and then they want to test them on European roads, and they find out that they actually have to start over the process of learning, or at least have to build in a couple of workarounds to make it work there. Another classical example is that you trained your method on rendered images on synthetic data. This was actually an idea that came up a couple of years ago, and people thought now we solved the data problem and the labeling problem because we can just render data as much as we would like to have. But it was actually found that if you do this, then testing on natural images is not exactly what you would expect. Yeah, so this generalization to this new data doesn't work so well. Also, few-shot learning is an example where humans are very good at. So it doesn't matter much whether you have seen 5 examples or if you have seen 1,000 examples. For the machine, it still makes a big difference how many examples it has seen. And this whole few-shot learning, although there are, of course, works that do this, are not as good as what we are used to from humans. And the question is a little bit, what do we have to do differently to get better on this? And one paradigm is self-supervised learning. It looks quite promising. Why is that? First of all, it makes learning shortcuts much less likely than if you learn with labels. You know, the problem is that with labels, you're too much bound to these labels, and it's then also sufficient to learn certain features that satisfy your training task with the labels, but it won't go towards any generic knowledge that is not bound to the labels. And that's less likely with self-supervised learning. Of course, you can also build shortcuts into self-supervised learning if you do it in a bad way, but it's less likely. And also, it's much easier to expand the distribution later because you don't need this manual annotation process. It's self-supervised, so that means you only need to find the data to learn, but you don't need to annotate this data. And before I go more into this, I first want to show that there is actually a task where all this self-supervised and also out of distribution learning works actually quite well. And this is the task of optical flow estimation. Well, I come from optical flow estimation, so that's why it's maybe not surprising that I come up with this task, but it's also an exceptional task in the sense that here we can actually learn on synthetic data, and it generalizes to real world data. Yeah, so when we started with this flow network, we trained it on very simple flying chairs that also became a data set that is now often used, where we just used random flicker images, applied some affine transformation, and pasted some chairs into them. And that alone is sufficient. You can extend this a little bit by real 3D motion, by putting some arbitrary objects into here, but also this is a purely procedural way on generating the data set. So there's nothing that requires some manual adjustment. In a way, there are, of course, some parameters, but then you can generate as much data as you like. And you see that this then also generalizes to new data without actually the need of any fine-tuning on real-world data. Of course, you can do better if you do this, but you get very reasonable results also just right out of the box when you train just on synthetic data. Yeah, and the same is true also, of course, for stereo computation. That's just a subcase of optical flow estimation. Also here you can train on the synthetic data and then can steer a robot on bush trimming from these disparity maps. Yeah, so the same story here. What's also interesting for these tasks is that they are not vulnerable to black box adversarial attacks. Yeah, so here we see a patch-based local attack. So you really paste the patch into the image. It could be also a physical attack where someone places a patch in the real world, and then this patch disturbs your optical flow computation completely. And if you build a very bad architecture, then this can also lead to some vulnerability, but it's actually not a true adversarial attack. It's actually more the aperture problem. That's what we found. So there's a paper from us actually at the CVPR where we show that you can actually also just use a normal stripe pattern and you get the same effect if you use a bad network that just has too few layers at the beginning, doesn't see enough context, and then you get this spread of mistakes beyond the local region that has been affected. Whereas if you use any of the more modern optical flow techniques, all of these networks actually don't have this problem. Yeah, so they can perfectly deal with these local attacks, and they are not attacked by that at all. And that's very different from recognition tasks. The same is true for also a global universal attacks. So that universal means that you're attacking the network with always the same pattern. So you have no access to the network itself or to the images, because if you do that, then of course you can always find a weak spot. But with universal attack, where you have a fixed pattern, you can only attack optical flow in homogeneous areas. And that's pretty obvious, because if there is no texture, then you also don't know how it is moving. And if you then add a texture that is moving, then it is of course picked up. But this is something that you can explain well. It's not really an adversarial attack. It's just a normal pattern that moves and that you then pick up. Then you see that also in the curve. So you have to make the epsilon of that attack really strong and also visible to make the error increase. So that also shows that this optical flow estimation is different from the recognition task that we usually deal with. So why is image classification different? So why is optical flow and stereo so special? And the thing is that they are both correspondence tasks. So that means the features that you learn here, they are determined based on how well they serve matching. A good feature is a feature that can be used for a unique matching. And that's also what you see actually in these architectures here, where you have these cost volumes and you have an explicit correlation here between the features of one image and the features of the other image. And you'll actually learn these features here in such a way that this correlation output here is then something that tells you something about the matching. And that's also the loss that you use to learn these features. And you only learn priors for resolving ambiguities. For example, that you don't see any structure or you have occlusion, then you have to learn explicitly on how you have to fill these occlusion areas or how you have to fill the regions where you don't have texture. So these are domain specific, but all the rest is actually something that is very generic and therefore also generalizes from one data set to another. On the other hand, recognition tasks are remembering tasks. So here you learn features that discriminate the training samples in the best way. And what's important is that these are the training samples. So it doesn't know anything about how the test samples look like and how you would best discriminate them. It only looks for features that solve the training task. And that actually makes us vulnerable to adversarial attacks, to out of distribution samples, and so on. Now, if we want to avoid this, what we can do is to find a way somewhere in between. So we could go to instance matching, which is already closer to optical flow because it's also based on some matching. And if you look at these two images here, these are from the same instance. They look very different because you see the object from a different viewpoint, you have different backgrounds and so on. So from the raw data, it's a very different image, but you also see that many features are shared here between the two images. And what you can now do is learn an invariance of these features so that really the features match between the two images. So what kind of variation can we expect? We can actually list this quite explicitly. So the pose can change, the camera parameters can change with which the image has been taken, the lighting can change, also the background, and there can be occlusion, so you don't see the full object but only part of it. And if you cover all these variations, then you can actually map the same different images of the same instance also to the same feature vector. The good thing is that most of this variation can also be simulated, at least approximately, by data augmentation. So if you do self-supervised learning on data that has been generated from a single image via these synthetic data augmentation transformations, then you actually you are learning invariance to these transformations here. And ideally, you learn a feature embedding that contracts then all these instance variations to a single point. And that means no matter which image you get as input, you will always get the same feature vector. And what's now different to normal recognition is that this concept here can potentially generalize to completely new data. So here we learn it, for example, for this red car, but you could actually learn this invariance to these transformations. This learned invariance can also apply to features from another image with another object. And that means you can then generalize to new objects that you have never seen during training, and this whole out of distribution problem is gone. So that's the idea why this instance matching here has some advantages over the classical supervised learning on class labels. So we actually already did that quite a long time ago, at least this basic idea that you apply transformations to single images and that way learn some invariance to these transformations. That was this exemplar CNN from 2014. So the learning strategy was a bit different than what you do today with the contrastive losses. So there we just trained a CNN to discriminate surrogate classes, which we then generated via data augmentation. So you take a single image, doesn't need any label, and then you apply transformations to this image, and that generates an artificial class. You do this now for many images, let's say 2000 images, then you have 2000 classes. Now you learn to discriminate between these different classes, and that gives you features that map all these images to the same point and different images to different points. And that already yielded quite good features to match instances. Of course, the learning machinery at that point of time was not as good as it is today. And today we would use some contrastive learning on synthetic transformations to implement this. So this is, for example, one contrastive loss. There are a couple of others with slightly different detail settings, but the idea is always the same, that you have positive pairs, so things that should belong together, that should map to the same point in the embedding space, and you make them contract in the embedding space, and you have some other points that don't belong together and you push them away. Actually, in practice, this is more for normalization. So actually, mainly you need these positive pairs that should get contracted, and you need some normalization procedure to make sure that not everything contracts to a single point, but only those points that belong together. Yeah, and the positive pairs are typically established via this synthetic data augmentation, which corresponds to instance matching. Yeah, so contrastive learning actually fosters instance matching. Now the question is a bit, why is this good for classification? Yeah, so there have been many recent works now that show that with purely self-supervised training schemes, you can then actually even cluster the features and get out kind of the classes that you would expect in the images. And yeah, that was also a bit surprising to me, and I wondered where this comes from, because so far we learned only at the instance level, so we didn't know anything about classes. Now here's my answer to this behavior. The question is a bit, how different are instances really? So if you have one class and different instances, are they really much different? So here are two examples that actually share quite many features, although these are two different cars. Yeah, so they have the same color here, but they are different brands, and they have different wheels and so on, but there are many features that are quite shareable. And that means much of the variation that you see here is already covered by these instance transformations that we learn to be invariant to in the self-supervised learning. There are, of course, also examples like this, where you have two very different airplane types and that hardly have any features that they share. They both have wings, but the wings look very different. They have tails, but the tails look very different. Here the wheels are visible here. The plane has wheels, but they are not visible at the moment. And so here you actually hardly can make any matching at the instance level. But these larger differences are often covered by transitivity. So if you have now a whole set of examples of airplanes, then there are airplanes that are very similar to this one and others that are very similar to that one. And then there are some on the way that link these clusters of similar airplanes, yeah, because also airplanes have evolved, so from this type to a more modern type. And via that transitivity, you can still link actually all these different features of the same class. And contrastive learning actually respects this transitivity. It might be a bit hard to control, but it's in principle possible. And this explains why self-supervised learning also works at the class level. Yeah, so for example, the work from Caron and colleagues from last CBPR showed that quite well. And many people are now building on these features for clustering. There's one caveat here, and that is localization. Yeah, so the explanation that I showed before actually requires that there is a single dominant object in the center. And this bias actually exists for ImageNet quite clearly. Yeah? So if you look at ImageNet images, just the way on how the data set was collected, it typically has a single object class in the image, because otherwise it would have been hard to label it with a single class. And also typically the way the picture is taken, typically the object of interest is in the middle and also fills the image quite clearly. And this is effectively like a bounding box annotation. And this is also exploited by these self-supervised learning augmentations. For example, if you think of the center crop and multi-crop strategies, they only make sense if you have a data set like this. Yeah, and possibly this is also required for all this contrastive learning to work at the class level, that you actually have some of these localization biases in your data set. Okay, so this is how you get features that cluster together at the class level. Now you still want to give the clusters a name. And of course, you could now just assign class labels manually again. But actually, this whole labeling is a bit arbitrary. And currently, the trend goes more towards using full text descriptions. Yeah, so this image text pairing is actually a much more powerful and also more natural way of labeling, because you can describe far more details than just a single label, which might not even be clear which label you want to give it in some cases. And the big advantage is also that often these pairs already exist naturally in the data and also in large numbers. So that means you can also use self-supervised learning again. So for example, often images come with captions, or at least have some tags in internet photos. When you have videos, there are often subtitles and sometimes even video descriptions for visually impaired people, or you can use speech recognition in videos, and all these ways to actually generate image text pairs are completely free and means that you don't need any manual labeling. The problem with this, though, is that the pairing can be noisy. Yeah, so it's not clear that you get perfectly clean image text pairing. Sometimes you also get a text that doesn't tell anything about the image and vice versa. So here's just an example for such paired image and text. So for example, you can search for an image of a dog on a red skateboard, and then it gives you all these different images here, and you see it's actually quite accurate. So it gets you examples that fit very well to this text description here. And if you do that in multiple ways, then you can actually generate a data set that you can use for training. And this has also been done, though there are multiple approaches to this. Probably the most popular one is the CLIP approach, which, first of all, it's quite successful. It was trained on a large set of data, and it's relatively simple and easy to understand. So what you do is you just have this paired data with text and images, and you train an image encoder and a text encoder from scratch. So you don't need any initialization or pre-trained model or anything like that. And all you do is actually make sure that the corresponding image and text leads to a high similarity in the end as the output of these two encoders. and higher than other images and text. So they have a lower similarity. So it's this usual contrastive learning signal, and we are just using the pairing between image and text as the signal for the positive pairs. Yeah, and with this, you can now also do many things. For example, you can build a zero-shot classifier by creating now a text prompt by using the label text of the classes you're interested in. For example, here, plane, car, dog, and so on. You feed that into the text encoder, it produces an embedding, and then you also have the feature embedding of your input image, and then the entry here with the highest similarity is then the output or the class output of this image. Yeah, so that's how this principle is working. Yeah, it's actually very simple. The only thing you need is actually a lot of data to train this. An alternative for those people who don't have a large data set that they can download over multiple months, and also where they don't have the compute power to actually train such a huge model from scratch. That's an alternative is to use actually a pre-trained text encoder and a pre-trained image encoder to already start with good features, and then just learn a projection network for both of them to use the same contrastive loss. Yeah, so then all the learning is actually only happening in the projection network, and you assume that you already have good pre-trained image features and good pre-trained text features here. Of course, this is more limited because if a certain important feature is missing here in these pre-trained encoders, then you also cannot learn it from this paired data anymore. Yeah, so the projection network is most likely not able to learn this anymore. So that's why the from scratch training is actually more attractive, but it's also less attractive from the compute that you need. And that's why many groups who want to study the science and don't want to put a lot of effort into compute enjoy this approach here much more. If you are working with this latter approach, then there is a work that we did last year where we consider that when we learn this joint embedding between image and text, or in this case it was video and text, then you actually ignore that also you want to keep also the original embedding space or the structure of the original embedding space. So let's say you had all the tomatoes in a similar corner of that embedding space in the video. Then in the joint embedding space, you also want to have the tomatoes together and not spread all over and just have the word tomato and the image tomato together in the embedding space. Often this anyway happens because the word tomato already clusters these things, but there are also many examples where visually you have the things clustered together, but they might be split up again via the text. And you can do this by explicitly keeping the similarity of the samples consistent via the negative pairs. Yeah, so instead of just having these positive pairs between image and text, you can also have, and the negative pairs between the modalities. You can also, oh, that's this one here. You can also have negative pairs that make sure that different things in the original embedding space also stay different, and those that are close together should stay close together. Okay, summary of my talk. So self-supervised learning enables open world generalization, or at least it's a good way to get there. A powerful learning queue comes from instance matching, so that you're actually looking at the same instance and its variations that are possible, and these are actually quite limited. And this can even lead to class level embeddings via the transitivity in a data set, yeah, because you have many samples that are different instances, but some of them are quite similar, and that's why they connect the whole class in the end. And in the end, I've also showed that image text pairing gives you an even more powerful learning queue that is currently started to get used quite excessively in the community. Thank you very much for your attention, and I'm happy to take questions.
Thank you so much, Professor Brooks, for the excellent talk. Any questions online or in the room? Please go to the mic.
One question. We have a lot of things, a lot of that there might be multiple.
I cannot hear you very well, I must say.
Yes, now.
I can hear you, but not the person who asked question.
Probably you can come up here. Probably you can come to the podium. And... Can you hear me now?
Yes.
Okay, sorry. So I would like to ask if you have a lot of images and a lot of text for them, then there might be multiple images which perfectly can be matched to the same text. Then what can you do in this approach then? Is it not disturbing the learning process?
Well, if they are matched to the same text, then probably they also have semantically the same meaning, or at least very similar meaning. So that means you actually want to put them into a similar corner of the embedding space at least. And there might be other samples that don't match them, or there might be contradictions based on other samples. So that's why they might not perfectly be at the same point. Why do you think there is a problem?
I think that the loss is punishing, making them close to each other because they're not there. It's not their original label.
You mean as a false negative because there's a negative pair?
Yes.
Yeah, that can have an effect, but it's relatively small because the negative pairs are very often outnumbered than by many other negative pairs. And actually recent findings also found that you actually don't need really these negative pairs. So there are also other normalization procedures in this contrastive learning so that you actually don't need to explicitly contrast it with other samples, but you can just take the positive pairs and then make sure that the rest of the space doesn't contract to a trivial solution. And in this case, you get rid of this problem. But it was anyway never a really big problem because, yeah, as I said, so there are so many negative pairs that such a case wouldn't have a super large effect.
Thank you very much.
Thank you. Any other questions? Perhaps you can try the mic again.
Hi, Thomas, can you hear me?
Yes.
So the initial discussion you had about correspondence and flow in contrast to classification, that was very interesting. I guess another difference between optical flow and stereo compared to traditional image classification is that the former is a task that is trying to recover some sort of physical property of the world, so to speak, whereas the latter is basically sort of human-defined categories, which may be, I guess, fuzzy and ill-specified in some sense. Do you think that has any role to play in the different generalization properties?
Yeah, of course, it's very different tasks in a way, because in one case, you're thinking of a clustering. If you regard it from an unsupervised learning perspective, it's a clustering process that would correspond to the classification, and the other one is a matching. So where you try to find similar pairs, and these are two different tasks, but they're also not that different in the sense that in both cases we try to find features that make things that match together have a high similarity. And that way, the whole learning that we are doing is actually a learning to shape the embedding space such that these similarities fit together. And although these two tasks are very different, the principle of learning the features in a way that the feature learning generalizes is something that you can carry over from one field to the other.
Thanks.
But I agree that the tasks are different because clustering and matching are different. In matching, there is a partner, and you just have to find it. And in clustering, you don't know on how many partners you have and where they are. So yeah, that's of course a different task.
Any other questions online or offline? Okay, I think I have one question. So it's very interesting to trying to learn a common kind of embedding space for image and text, but sometimes, I mean, a lot of the times, text has ambiguities. And then in the common embedding space, there may be contradictions, right, between text and image. So, for example, in the original image embedding space, the distance may be far between two images, but then in the text embedding space, they may be like close. Do you see that as a problem or a challenge?
Yeah, definitely it is. And that's probably also the reason why you need so much data to learn these models successfully, because actually it should not be necessary to have millions of image text pairs to learn about a little bit of text. But the problem is that you actually need this amount of data to statistically level out these noisy samples that you have in these pairings. And it can be even worse. So if you think of YouTube videos, very often when the people talk about what they are currently doing, they're actually talking about something completely different thing, so that you don't see in the video. And this is complete noise, and you actually have to, the learning procedure has to learn to ignore this, which is probably quite hard to do because it doesn't have any manual learning signal. So yes, it's actually just the amount of data that statistically removes this noise. At least that's my understanding. I might be wrong, yeah. So there might be other signals that help here.
Thank you so much.
I guess that's a challenge of the coming years to actually find ways on how to deal with this noise in a more efficient way, so that you need less data to do the same.
Right. Thank you. Let's thank Professor Brooks for the talk again. Thank you so much.
Thank you.
Okay, coming next in the program, we have our paper presentation with the title Visual Domain Bridge, a source-free domain adaptation for cross-domain few-shot learning. Is there any author of the paper here?
Hi, yeah.
Can you share your slides?
Yeah, yes, sure. It's me. Okay, so the paper title is Visual Domain Bridge, a source-free domain adaptation for cross-domain few-shot learning. So despite the significant achievement of the deep learning methods, its performance always degrades under the distribution shift, and there are a lot of approaches and methods to alleviate this problem, and but mostly they require samples from the target data during the training time, or samples from source data during the test time adaptation. By approach and methods here, I mean domain adaptation techniques, actually. So and batch normalization is a common approach and a common component inside deep learning models and deep learning architectures. It boosts the training convergence and reduce the training time sensitivity to the hyperparameters. Its main duty is to normalize the intermediate feature maps, intries, let's call them H, of each batch of data based on mean and variance of that intries. But what happens when we apply a covariance shift or a distribution shift to these batch norm layers? Let's suppose we have a target data with covariance shift, with distribution shift, sorry, and we apply our data to our trained model on a different source domain. In this case, we will normalize our feature maps interize based on a mean and variance, which are not good and correct for our targets data, because we have a statistically distribution shift in our target data. And this will always lead to a representation gap at the output of our deep model, and this is a well-known source of performance degradation. Most of the methods here in the domain adaptation section are always based on aligning our model to our target data, which these models mostly requires a lot of data or a lot of computation during the training time or adaptation time, which are always impractical in real world scenarios. Here, we propose a different perspective and different approach to solve this problem. We instead of we adapt the target data instead of our model. So we move our target data statistics toward the source data instead of adapting our model to the target data. During this process, we transfer our target data statistics toward our source data, but not replacing or moving them completely, just moving them toward and making them more similar and near, because we have some affine parameters that are adapted during the training time based on the source data, and we cannot neglect their role inside the batch norm layers. I will explain this in more detail here. So we have a target data HT, and we normalize our target data inside new layers, let's call them VDV, based on our statistics, which is statistics mu and sigma, are calculated using a weighted average of our target data and source domain. So we don't have source domain samples, but we have mean and sigma inside our batch norm layers. And after normalizing this, we move our statistics toward the source data statistics by multiplying them to sigma and summing up with means. Then we use the transfer target data to normalize and calculate the whole batch norm, as we can see in equation 8. And here mean and sigma are calculated again using a weighted average of the transferred data statistics and source data statistics. We have conducted a lot of evaluations and experiments to evaluate the effectiveness of our method. And one of them is evaluating the representation gap, role of our method on the representation gap. And we can see, so let me explain this plot a little more. We have a pre-trained model, pre-trained on ImageNet domain. Then we fit this model with ImageNet samples, and this is the blue color. Then we fit this model with another data set, samples from another data set with a distribution shift. This data set here is Euroset, which is the orange color. And then we replaced all the batch norm layers with VDB, and then fit the model with the Euroset data set, and we have the green model, green color here. We can see that the model with VDB has a lower representation gap compared to the model with batch norm, you can compare the green and orange colors. Also, we conducted another experiment to analyze the visual transfer effect of this VDB layer instead of the batch-norm layer if we substitute it with batch-norm layers. And we can see inside the pre-trained autoencoder, pre-trained on ImageNet, if we replace the encoder parts batch-norm layers with VDB, and fit with different type of data sets, which are visually different from ImageNet, we can get some similar outputs to the ImageNet's image. Something like natural image, daylight image, and something like that. And an interesting thing here in this experiment is that our samples from ImageNet are invariant to VDB. It means that VDB doesn't affect ImageNet's near domains. And we have conducted a lot another numerical experiment on the CDFSL benchmark. It's a tough benchmark on the cross-domain few-shot learning. First, we conducted this experiment using a ResNet 10 pre-trained on ImageNet, and we can see that VDB is superior to all other batch norm-based source-free domains, source-free methods, and also it can improve other methods like startup, which is a super heavy method in CDFSL benchmark, and FN as well. So it can be combined with current methods and improve their performance. And we repeated this experiment using a ResNet 18 model pre-trained on ImageNet, and we can see that it is superior. Our method is superior to previously batch norm-based source-free methods with a bigger margin, and it's still able to be combined and improve other methods too. More details and values are available on the paper. I try to make the slides as much as possible as summary. So thank you for watching and your time. I will happy to hear your questions.
Thank you. Any questions from the audience? Okay, so I have one question. So, I mean, do you have any assumption on the approach, like, you know, under what scenario in the real world scenario it will fail, for example?
So actually, no. On all of the data sets that we have explored our methods on, evaluated our methods on, we saw a notion of improvement, even in near domain setting, and or even in unseen ImageNet samples. It means exactly inner domain setting. It improves the results, of course, in few shot setting, but it needs more evaluation on other settings, like, for example, non-few shot setting when we have a lot of samples, and we should consider them to see what will happen with this method.
Okay, thank you. Next paper is class-wise thresholding for robust outer distribution detection. So authors, please share your slides.
Yeah, sure. Oops, 1 sec, please. Something is going wrong.
Take your time. We have 5 minutes of transition time. Yep, we can see your slides.
Yeah, but is crashing? I'll change the software. Let me see. I have the PDF of the slides just in case. Can you see the slides?
Not really.
Oh, really?
Most of the part is black, and then we see some gray out region as well.
Can you see the screen at least?
We can see the screen and like a not responding mouse cursor.
Oh. I'll stop sharing and reshare again.
Sure.
How is now?
Not yet. Okay, now we can see.
Can you see the slides moving?
Yes, we can see the site.
Okay. I have no idea what's happening. I'll try to change device. It's crashing.
We were able to see the slides okay, but it was crashing, you see?
Yeah, my Zoom is crashing and reloading again.
Oh, okay.
Now, can you see the slides now? But it's still crashing. Just a second, just a second.
Sure, right.
Hi everyone, so I'm here again.
Now we can
Okay.
see your.
Yeah, I'm sorry. Okay. Okay. So hi everyone again. I'm sorry. I'm Matteo Guerrero, PhD student at the University of California, Berkeley, and I'm going to present the paper called Class-Wise Thresholding for Robust Out-of-Distribution Detection. So the context is the out-of-distribution detection task in the supervised multi-class classification scenario. Most of the real-world application break the closed-word hypothesis, meaning that data at test time are sampled from a different distribution with respect to a data training time. Indeed, fed with the unknown data, this classifier can make wrong prediction. And for this reason, many detectors have been previously designed to spot and reject OOD. So our contribution can briefly summarized in 3 points. So we were the first in identifying a new problem, namely that OOD score depends on the predicted class. And this is made worse by the fact that existing OOD algorithms assume no label shift. To solve this issue, we design a new plugin for any existing detector, which improves their robustness. And finally, we have also assessed the performance limit of the current approaches with and without our plugin. OOD detection is just essentially a binary classification problem between in distribution ID and out of distribution, so OOD samples. And every detector is just a function that produces a scalar score on which we need to set up a threshold using just ID data, since OOD data are, for definition, unknown. And the most used approach to do that is the constant false alarm rate scheme. So a constant number of ID samples are always classified as OOD. So as already mentioned before, we notice that OOD score depends on the predicted class. So when using a unique threshold, the orange one, the constant FAR is guaranteed only for all the classes together, not for every single class. So every single class could have an arbitrary high level of false alarm, which cannot be predicted beforehand. So for example, in this figure, given a detector, the max logic detector, we choose a 5% constant false alarm rate to set up the orange threshold, as in the literature. And in green, instead, are highlighted the 5% false alarm rate for each class. And as possible to see for the first two classes here, the class cat has the green line above the orange one, meaning that its FAR, so its false alarm rate, is higher than the overall one. And vice versa, the class dog has its FAR lower than that. Moreover, as mentioned before, a common situation present in a real scenario is label shift. So prior probability of each class changes between training and testing. This means that, for example, in the task of classifying like two class, so cats and dogs, there is an overall higher ratio of cats, or just one class, in the test set than in the training one. So this causes an issue, and the issue is that due to the label shift, the overall false alarm rate can fluctuate if at test time we have to classify only a subset of the classes. For example, if we have to classify both man and car, the overall false alarm rate will increase, since the green lines here of these three classes are higher than the orange one, that is the overall one. So more sample than expected will be classified as OD. And moreover, malicious attacker can exploit this weakness to launch attacks that in general may cause an overflow of false alarm, eventually lowering the sensitivity of the detection system. So how to solve this issue? So to avoid the brittleness of the false alarm rate that was intended constant and overcome the problem that this could bring, we propose to use k different thresholds, one per each class, rather than just one. So one per each class, the green one, rather than, as in the literature, the orange one, just one. These are set using the same constant false alarm rate criterion as the orange one. And as we're going to see, our approach that we call multi increase the robustness of the overall OOD detection system. So we will analyze the result using two metrics, the most common one. So the false alarm rate, namely ID in distribution classified as OOD, and later misdetection rate, that is OOD classified as ID. So 1,000 different scenarios have been simulated, forcing label shift, and the false alarm rate per each class was reported in the figure. There we compared the one threshold scheme above with ours below. And so we can see 10 different histograms of FAR, one for each class, in different colors. Our solution yields two main results. So it guarantees a stable FAR. Stable FAR. So both for each classes and for the overall scenario. In fact, in the second subplot, so the one below, all the histograms are overlapped, close the constant FAR chosen to set up the threshold, as opposed to what happens for the one threshold in scheme above. Moreover, our solution limits the maximum FAR achievable by a class, making the system more robust. So here, on the contrary, like for example, one threshold scheme could downgrade the detection system, bringing false alarm rate here in the example with the cipher 10 up to 12%. So 1,000 minus 88, 7 point percentage is higher than the intended one. The other block of result is the one related to misdetection rate, where we have empirically demonstrated that our approach that has gained before in reliability do not lose detection performance, since the misdetection rate for the two approaches, so the one on the left and ours on the right of the bar, are very similar. And then we produce these benchmarks that this comprehensive benchmark that could also guide the designer in the choice of the best detector for a real-world application mainly. So to conclude, the main contribution of this work has been raising awareness on interclass performance discrepancies and false alarm robustness resulting from OOD detection algorithms, which have never previously discussed in the literature. And as we have seen, currently introduced technique can have very undesired consequences in practical use. So thank you so much for your attention, and I'll be glad to.
Thank you. Any questions from the audience? Let's see whether there are texts. Okay. For online audience, if you have questions, you can text in the chat. Okay. I have one question. So, so since you're proposing to use multiple thresholds instead of one, do you see any drawback with this approach? Any, undesired side effect from this approach?
Yeah, the only limitation that I can see is that to use multiple threshold, you have to have a given number of sample per class. So you cannot have like very few sample in just one class and like a lot on the other one. So you have to have like kind of a balanced number of sample per class, or at least not a class with very few sample, because when you have very few sample, you are not able to set up a good threshold. That's it.
I see. So let's say if we are deploying this algorithm in the real world scenario, and then it's unavoidable. Sometimes you do have classes with very few samples.
Yeah.
What would be a potential workaround?
Yeah, like use the like for example for that class, when you do not have like a lot of sample, you can use the the mean of the other thresholds. You know, you can use just like custom threshold for each class, and then when you have a class with not too much sample, you can use their mean. So return to the orange one.
I see. Okay, thank you.
Thank you, everyone.
Okay, and coming up next, I think it's the paper on is neuron coverage needed to make person detection more robust. Can the authors please share their slides?
Hello, can you hear me?
Yes, we can hear you.
Okay, I'll share this. Is this the correct one? Do you see the slides?
Yes, we can see the slides.
Okay. So I'm Svetlana from the FZI Research Center for Information Technology in Germany, and I'd like to present the results of our work on neuron coverage applied to person detection. Yes. So our work is motivated by the need to ensure that neural networks are safe, in particular in such critical scenarios as autonomous driving. And one approach that we were looking at is the neural network testing. For this, we looked at the strategy which additionally comes from the software development, namely it's the coverage guided testing. And the overall approach looks like this. We first randomly sample data from the training subset. Then we introduce natural and adversarial mutations to this data and find bugs among mutated images. And by bugs, we mean inputs that lead to wrong detection by the neural network. And then we retrain the baseline on these bugs to increase the robustness. And basically, this approach was already tried in the computer vision community, but mostly on toy data sets like MNIST and CIFAR. And our goal was first to apply it to the more real use case like person detection in crowded scenes. And secondly, we wanted to look at the necessity of including coverage metrics in the bug definition. So is coverage as introduced for the neural networks is really needed for this neural network testing. And for this, we started with two definitions of bugs. For the first one, we only require that a bug leads to decreased performance as measured in MAP for the object detection use case. And in the second extended definition, we also want a bug to lead to the increased coverage. And coverage was initially proposed by Pei et al. In 2017. So what they did is they looked at the portion of activated neurons in the neural network, and a neuron is activated when the activation function on a given input exceeds some predefined threshold T. And after that, further metrics were introduced, for example, the neuron boundary coverage. Here we basically look at the range of output values for each neuron, and in particular, we look at those which which fall into the upper bound part and the lower bound part. And finally, the strong neuron activation coverage, it only looks at the upper bound part of the neuron activation values. To ensure fair evaluation, we first did a split of the initial training validation data. And for this, we divided the initial train data into the train data itself, which we use to train a neural network, and specifically separated data for which is used for CGT for coverage guided testing. And we sample only from this data, not from the training data, which is used to train the network. And to evaluate the data, we first evaluated on this normal test data set. We then create an adversarial test subset where each input is substituted with the corresponding adversarial input. And we also test on the corruptions data, which include different types of corruptions as defined by Hendricks. And in order to generate bugs, we apply a set of randomly sampled mutations like flips, translations, and filter operations. And we also introduced these acceptance tests proposed by C et al. To ensure that semantics of the image is not affected by those multiple mutations. For the natural mutations, which include translations, flips, and filter operations, we did them in 2 stages. And the first stage, we applied those mutations to the randomly sampled images sampled from this separate CGT subset. And we then did it also at the second stage by mutating the already mutated images as also suggested in the state of the art. So our approach was evaluated on YOLO V3 model, and we used a crowd human data set, which contains images of highly crowded scenes. We resplit this, the data set as I described before. We did those natural and adversarial mutations to find bugs. And in the paper, we do not report the MAP for the retrained models, but we only report the relative change in MAP. And so basically, we first measured the MAP on the on all test subsets and the neuron coverage on all test subsets, and then we only report the difference. So what we could see, we basically retrained models with different thresholds for the bug definition and with different neuron coverage metrics involved, and also without neuron coverage metrics. And what we could see is that models retrained with natural mutations also improve robustness against adversarial images. And also, as expected, adversarially models trained with adversarially mutated bugs are also, they also exhibit greater enhancement of the robustness against adversarial attacks as expected. But the most interesting part was concerning the coverage matrix. Actually, we could see certain changes of neuron coverage for the retrained models when compared to the baseline, but it was not consistent with the gain robustness at all. So sometimes we could observe the drop of the neuron coverage, but it was not consistent with increase of the robustness or with the decrease of the robustness of the model, be it against natural or adversarially mutated images. And this is also consistent with the work for the image classification models on these toy data sets. So here are also examples of these bugs that were found. You can see that the model is struggling to do correct detections on the mutated images, but the retrained model is again robust. And the same also applies for the adversarial mutation. So to sum up, in our paper, we applied this testing of neural networks with and without coverage. And the testing itself, it led to the increase in performance, also for adversarial and naturally mutated models. But we can see, we could see no evidence that coverage metrics help to improve robustness, which is also consistent with the related work for the MNIST and CIPHER datasets. Thank you for your attention.
Thank you. Any questions online or in the room? Okay, so So I guess in your conclusion, you're saying that the coverage metric doesn't indicate, or I mean doesn't correlate with robustness improvement, right? So
Yes.
From a practical perspective, what do you think that could be the takeaway message here, or like how could coverage metric be useful for development of computer vision algorithms?
Well, basically, I think that the takeaway message is that this assumption that appeared in 2017, that we can look at the portion of activated neurons and make more neurons activated. So the more neurons are activated, the better is the network. It does not hold anymore. And basically, for the future, we need to concentrate on other methods to test neural networks.
Thank you. All right, if no other questions, I think we're gonna have a break session and then we will resume at 10:45. Thank you so much. Okay. Okay. No, I think so.
Okay, so hello everyone. Welcome back to the workshop. Our next speaker is Dr. Wang. He's a senior research scientist with NVIDIA. His research focus is on generative adversarial networks with application to generating synthetic images, high quality video manipulation, all those things. His research won the Best in Demo award from SwiftGraph 2021. He also won the Best Reviewer award at CEPA 2021. So let's welcome Dr. Wang and let's start. No, sorry, I was just looking for audio. He said that share the screen again and then share the audio. Not what is the audio?
For the method, on a very high level, our network takes the source and driving images as input and generates two sets of 3D key points. These key points are then used to predict a flow field, which is used to warp the source features extracted from the source image. The warped feature is then passed to a generator to output the final image. The most novel part is how we estimate the source and driving key points unsupervisedly. We decouple the estimation process into an identity branch and a post branch. In the identity branch, we use the detector to estimate canonical key points. Note that this only encodes the identity information and is independent of poses and expressions. Next, in the post branch, we estimate the hair rotation, translation, and expressions. So these parameters are then used to transform the canonical key points to obtain the source key points. And similarly, for the driving image, we apply the post branch to get the post information. Since the identity is the same, we reuse the canonical key points from the source image and transform them to obtain the driving key points. These two estimators will share weights in our network. Here is a visualization if we use the intermediate key points to synthesize the output. We can first predict the canonical view from the canonical key points. Then we can use the parameters to apply rotation, translation, and expression information sequentially to obtain the final driving image. This enables us to create a compact representation for video transmission. We can now decompose the frame into a canonical view, which is fixed throughout the video, and the varying parts are only those parameters: the head pose and the expressions. So transmitting only these parameters will require much lower bandwidth than transmitting the actual RGB pixels. Finally, our model also has some other additional applications. First is that we can animate the portrait paintings, for example, using photos generated by StyleGAN. Combining it with audio to face, we can generate face motion videos given only voice as input.
We're going to play a wonderful game called Who is Your Daddy and What Does He Do?
By changing the pupil key point positions during synthesis, we can easily manipulate the gaze directions as shown here. Okay, so that concludes the first part of the talk. And next, I'll introduce how we create the avatar using multiple images. So the first question is, we can already do pretty well using just a single image to reconstruct the videos. So why do we want to use more images? To answer this question, let's first look at an example. So in this, suppose this is our source image. The background is occluded by the person. So we don't really know what the background looks like behind this person. So in this case, if we try to reconstruct the driving video, then the network will try to generate some background, but not very ideal, as shown here. So instead of doing this, if we had multiple reference images as input, like in this case, suppose we have two different images and one contains the background, then it becomes much easier for the network to synthesize the background. This is the result comparison. You can see that if we only use one source image, the network will struggle to synthesize the background. But if we have two source images as inputs, the network can synthesize the background more correctly. Okay, so you might think, that's just the background. What about faces? It turns out this is actually very beneficial to faces as well. Let's look at this case. So in this example, we have three different source images from different viewing angles. They capture different parts of the face. So if we try to reconstruct the driving video shown on the left at the frontal view, then all three reconstructions look very well because they can all see source 1, which contains the frontal view of the face. But when the driving video turns his head, you can see that output using only one source will generate weird results because it cannot see that part of the face. And if we even turn the subject's head to another direction, then output using two sources would fail as well. And only the outputs using all three sources can faithfully reconstruct the face in all three different directions. Okay, so this is an even more extreme case where this subject is wearing an earbud on his right ear. And obviously, the reconstructed result using only one source will fail to reconstruct this earbud. And the outputs using two sources would more faithfully reconstruct the earbud as in the driving video. Okay, so that's for video reconstruction. We can also apply this method to cross-identity motion transfer as well. So in that case, we found that using multiple sources also help with the motion transfer. So here's an example. You can see that ours using two source images perform much better for both the person and the background generation. Here's another example. So in this case, the two source images, one has the eyes closed and one has the eyes open. So our reconstruction can more faithfully reconstruct the eyes color, while the other methods, because one source image has closed eyes, they would fail to reconstruct it faithfully. And next, we can also visualize where the output features are borrowed from the source image. So in this visualization, when we have the mouse click a point on the output, it will show that where in the source image the feature is borrowed from. So kind of like finding the correspondence between the output and the source. However, you can see that the left ear is not visible in the source image. So when we click on that, it actually look up in the right ear position to reconstruct the left ear in the output. And when we have multiple source images, the network is able to detect whether the output is visible in both sources. If yes, then the network will use both sources, and if not, you only use the source image that contains the visible region in the output. Okay, so finally, once we have this avatar, we can put it in any virtual background. But before we do that, we also need to relight the face so it can look more natural in the new environment. So this relighting actually has many different applications, such as changing the background in a portrait image, enhance the lighting condition, create cool visual effects in movies, and in video conferencing, we can use virtual environments. Here is one of the use cases where we can place the avatar in a virtual environment and also rotate the background so it feels like the subject is truly in a different environment. Here is another example where we can again place the different subjects in different virtual environments. Okay, another use case is that if the input video is not very well lit, for example, if it's dark and there are shadows on the face, we can also enhance the lighting and make it look more professional. So after the relighting, the output video looks more like it's recorded in a studio instead of in a normal place. And finally, we can simply replace the background in a video, which is very common in video conferencing nowadays. But if we only replace the background, it will feel very unnatural because the color tone wouldn't be right, but it becomes much better after relighting. We can also use some fancy background to create some cool effects like shown here. Okay, so to summarize, using just a single image, we can animate the face and control the head pose and gaze directions, creating a digital avatar that can be used for many different applications. And furthermore, if we can access multiple source images, we are able to create an even more complete description of the scene and the subject, which can often result in better synthesized results. And combine this with relighting, the avatar can be put in any virtual environment, which enables much more applications. Thank you very much for your attention.
Yeah, so next we have a couple of paper presentations. The first paper is they see deepfake source identifier for social media. Is there any author there?
Yes. Hello, am I audible?
Yeah. Can you share your screen?
Sure. Is my screen visible?
Yes, it's completely visible. Maybe you can put on the full screen mode if it's there. Then.
Just a second. No, I'm unable to do that, I guess.
Yeah, it's fine otherwise.
So good afternoon. We present DAISY, a novel deepfake source identification algorithm for social media. So what is deepfake? The term deepfake is actually a portmanteau comprising of the words deep learning and fake content, which essentially translates into generating synthetically altered media content by employing various deep learning architectures and frameworks. Now, such type of videos, false videos can be employed to damage reputation and as well as spread false propaganda, which was ubiquitous during the US presidential elections of the Russia-Ukraine war. And if such type of misinformation is not contained in time, it can generate a narrative which is actually very far from the actual truth. And although rumors are spread by a handful of individuals, it is extremely difficult to pinpoint at the source of the deepfake tweet. And it has been established in previous studies that cutting important links to the network can help in controlling the rumor propagation. And hence, the identification of source is an important task here. Also, we have specifically chosen Twitter as the social media platform that we want to target because of its credible nature, the mature audience that is present, and the aggregation on breaking news on it. The key contributions of this research is source identification of a deepfake tweet, virality estimation, which indicates the degree up to which the tweet will spread in the near future with the help of a retweet count per minute. Additionally, our portal can be used by law enforcement agencies to maintain a vigil on the spread of the fake content on Twitter platform, which enables them to prevent upheavals in the society. Furthermore, our portal can be extended to include information about the demographics of population where deepfake has reached and help in taking localized action. Our algorithm can also search for deepfakes for a person. Let's say we want to find deepfakes of a US president like Donald Trump or Joe Biden on Twitter. So we can import an image of Donald Trump and fetch all the deepfakes of Donald Trump, and these can be then visualized by a source directed graph, to give a better understanding of the current situation to the user that's using a portal. So this is the overview of our algorithm. Our pipeline basically consists of 3 modules. Firstly, we fetch tweets from the Twitter API by using a text query or a hashtag. And by this, we can fetch all the tweets that are relevant to the given text query. Next, various filters are applied on the extracted pool of tweets, and we perform deepfake detection on it. Here also we can look for similar deepfakes for the given image if it's provided. And at last, the source is detected, and virality, which is the retweet proneness, is estimated for all the tweets in the filtered pool of tweets. And to give the user a greater insight into the network, we presented as an output graph showing the links between the tweets, which is shown below. Now coming to the first module of our pipeline, tweet filtering. Basically, from the extracted pool of tweets, we discard those tweets that have only text in them, as here our main focus is to isolate deepfakes which necessarily contain media in them. And also here the retweets are replaced by the source tweets, as your primary objective here is source detection. And if an input image was utilized, all tweets similar to it are retained and the rest are discarded, as mentioned before. Now, for defect detection and similarity, we employ exception-net architecture, which is the state-of-the-art architecture for defect detection. And our exception-net model was trained on high-resolution videos of face forensics plus data set. Now, coming to the similarity part, if you want to compute image-to-image similarity, we utilize the cosine similarity method. And this computation is performed only on the cropped images, cropped facial regions, and not on the whole image, which are detected by the MTCNN model. For feature extraction of the cropped facial regions, we use a light CNN model, which was created on the MS-11M dataset. And for computing video to image similarity, we compute it on frames and then take the mean of all the 10 frames that we have taken from the video. Now, the threshold for similarity was set at 0.4, which we concluded experimentally. Lastly, the unique source tweets are then sorted according to the timestamp. And generally, the top 1% of the sorted tweets is the probable sources. But it was also observed that the earliest source tweet in the network is at most times the suspected source. And we also compute the retweet count per minute based on the influential attributes of the user profile, let's say friends count, followers count, and the number of tweets that it have made, and so on and so forth. And we conduct experiments in two diverse settings, constrained and unconstrained. For constrained, we made like 5 Twitter users and made 70 tweets and 90 retweets. These tweets contained real and deepfake videos, which have taken from the face forensics plus data set. And for the unconstrained experimental design, we fetched 10,000 tweets from using the text query #Russia and #Ukraine. Now, some of the samples of tweets that we tweeted are shown here. And the motive behind this experiment was to analyze the scalability of our proposed pipeline on real-world tweets, as well as analyze the performance of our source detection algorithm. And here you can see the results of the constrained environment. These figures represent the graph that we output, with the big black dot showing the source of the suspected source of the tweet. The dark blue dot showing the source tweets, and the retweets are connected to the source tweets via links, and they are colored according to the difference in the timestamps. And while doing this experiment, we maintained a record of the actual source tweets and found that the predicted source matched with the actual source tweet in both modalities, using only text query and using text plus image query as well. For the unconstrained environment, 10,000 tweets were extracted to the given query, Russia and Ukraine. But due to the limitations of the API, it was not feasible for us to collect all the tweets that were related to that API. And here, no ground truth was available. Hence, we had to manually check the tweets of that contained that our model outputted. The images here to the left represent the possible deepfake tweets for the query, and the network graph represents the suspected source, all source tweets, and the corresponding retweets as similar in a fashion similar to the constrained environmental setup. Now coming to the use case and applications of our portal can be used to curtail the spread of misinformation in situations of war and elections. We can employ a text query that relates to, let's say, the US presidential elections, and all the deepfake tweets will be fetched that are related to it will be fetched, and the source of such false propaganda can be traced to prevent the masses from being influenced from false information. Similarly, we have seen that social media has a potential to influence the outcome of war also. And recently, there were many deepfakes circulated on Twitter of the Ukrainian president admitting his defeat. And this can lower the morale of the soldiers and actually prove to be very detrimental. coming to the conclusion, our paper presents a novel deepfake source identification algorithm, which is encased in a web portal for non-technical users to use it conveniently. And we have demonstrated its scalability in both constrained and unconstrained settings. And the algorithm has numerous real-life use cases and applications, as I've mentioned before, and it can be used by law enforcement authorities to take down deepfake content from social media and thus improve its trustworthiness altogether. So thanks for the time, and if I'd be happy to answer any questions.
Is there any question? Or is there any question online? Or maybe till the time, can you maybe explain what exactly you mean by the source identification? Because I got confused between its source is like Twitter versus Facebook, or a source means the original writer or author of the tweets.
So basically, the source here is the person or user that has first tweeted that deepfake on Twitter. So let's say if I have a deepfake and I post it on Twitter, and there might be cases where other users have downloaded that deepfake and then reposted it again. So the users that have reposted it are not the source, but I am the source because I have tweeted it first.
So
hope it clears.
Yeah, I think for the tweet wise, I think we can still imagine that, because Twitter might show that it's a retweet, or WhatsApp also showing that it's a forwarded message or something. But suppose if I download the video and then again post through my account only,
right?
The video contains any properties through which we can say that it's a downloaded and then retweeted or downloaded video?
No, because if you have downloaded the video, the source should be from Twitter, right? So basically, the first one who has tweeted is actually identified as the source, and you won't be classified as a source because you are tweeting after a certain time difference.
Oh, okay, yeah, thank you. Is there any question? Okay, if there's no question, I think we can close this. Thanks, Harsh.
Thank you.
So the next paper is doppler saliency towards more ethical person re-identification. Is there any author here? Okay, so welcome to the speaker.
Good. All right. Thank you for the organizers for organizing this workshop on a really important topic. I'm Anthony Hoogs, the Vice President of AI at Kitware. Kitware is a small software R&D company that's, yeah, you guys over. Okay, so Kitware is a small company that about 200 people now, so maybe not so small, a medium-ish company that does software R&D across a wide range of customers, mostly the US federal government, about 90% of our work, and 10% or so in commercial. So we have an emphasis recently on ethical AI and fairness in computer vision. That's come out of a lot of our work for a variety of agencies, including the Department of Defense in the US, which is mostly what I'm going to talk about today. We do a lot of work with DARPA, Defense Advanced Research Projects Agency. They're the ones who funded this work. And most people may not associate the Department of Defense with ethical AI, but they're really leading the charge in the federal government in the US side on implementing ethical AI in a very serious way, because there are very serious consequences for AI within the Department of Defense. There's very mission critical applications, armed autonomy, and all those things are faced for real. And the US government takes this very seriously, unlike many or most governments in the world with similar capability. I won't name names. So this paper is co-authored by Brandon Richard Webster, who did most of the work, and Brian Hugh, Keith Fieldhouse. We're all at Kitware. I'm here presenting this. And don't worry, I will explain what a doppelganger is. It's a strange word, I agree. Okay, so first, we're going to look at the re-ID problem and what the paging down. I'm going to spell the page down here. Okay, thanks. Okay, so first the re-identification problem, which is the setting for our work here. So this is a standard problem in video surveillance. It's not distinctly associated or uniquely associated with ethical AI or fairness, but we're taking a look at it from that vantage point. So first, the re-ID problem is cast usually as finding an individual in a large archive of video of typically of a facility or a large area. So you have a big archive of video collected from a bunch of cameras, and you have an individual that you want to find instances of in that large archive. And often this is in a streaming setting where you're collecting video online or in real time, but it can be archival as well. So on the left here is just one example showing of a query image of this one individual, and we would like to find instances where that individual appears in a variety of camera views over a period of an extended time where we might have hundreds of hours of video to search rapidly. So typically re-ID like this depends very much on what someone is wearing, their clothing, because that's most of what the appearance signature really is. It can also be done facially in some combination. We've done this too. But many times the face is not visible or the resolution on the face is so low that it's really quite difficult to do facially based re-ID. So it's relying on clothing primarily, which is going to become important because many times we can make mistakes in re-ID. So we can have two people whose clothing is essentially the same. And this happens a lot in uniform situations like this, where we have two people who are workers. They're wearing the same clothes intentionally. In this case, the clothes even have this yellow vest intentionally to keep them away out of harm's way in traffic. So these kinds of situations and many others make it much more likely that we're going to have an error in re-identification, right? That we're going to associate individuals incorrectly when there's actually multiple individuals who are wearing very, very similar clothing and look similar in body size and shape and so on, but they're going to be confused. And in normal re-ID circumstances, that's not potentially a significant problem. But if you're doing something a little more serious, like you're trying to determine whether someone is behaving in criminal activity, this can be a serious ethical issue. So sometimes you might see an individual who committed a crime in video, and you then look for that individual in all these other videos. If you make a mistake in re-ID, you could be tracking down the wrong person. So we have a couple of ways to address this. One is that if we see a lot of video, we can often know that there is a doppelganger pair. A doppelganger pair is where there are two individuals who look essentially the same, at least the same to the algorithm. Right? So they are visually indistinguishable, at least in some presentations. Now, we don't know that initially, perhaps, when we're watching all this video automatically, but sometimes those two individuals might appear in the same scene at the same time. So it's very definitive now. We know that we have this problem. We have these two individuals who previously thought were the same based on their appearance, but now we can tell that they're actually two individuals independently. So we call that a doppelganger alert, right? We can kick out something that says, hey, we found this condition, and we can alert the user that says, hey, you've got a problem here. Anything you thought you knew about this individual is now called into question because it's really two people. So if I was watching something that this person did, now I have to attribute that to one and not the other. So We looked at a data set here for re-identification called Mars, which was published a few years ago, not by us. And in that data set, there is a number of intentional confusers. Like re-ID is harder when you have people who look very similar to one another and you have this doppelganger condition. So these are examples here on the bottom of this doppelganger situation for two individuals on the left and two individuals on the right. You can see the clothing is similar, body shape, et cetera, are quite similar. Okay, so we want to be able to detect these doppelgangers and then alert the user that this condition exists. Okay, so we have a system that does this, and it presents these doppelganger pairs to a user. Now, when you look at these images, you might say, well, these really are the same people, at least on first glance, and that's why the algorithm thought they were. They're intentionally, obviously, in this condition, they're going to be very similar looking people. So we can help the user a little more by saying, well, let's use visual saliency to highlight the areas that actually distinguish these individuals. So we do a post-processing step on this doppelganger alert and compute visual saliency maps to show where these differences are computationally, right? And that's really the key contribution in this piece of work, is using visual saliency maps in this pairwise doppelganger condition to alert the user to say, these are the areas that the algorithm thinks differentiate these two individuals here. Look at these. And then you could confirm or not whether it's really a doppelganger pair, whether it is the same individual. So you can see on the right here, there's areas that are highlighted on each of the two individuals on the left. And those are the areas that are the most distinctive for distinguishing between exactly these two individuals and these two conditions. So as you might expect, we have a straightforward approach to compute this. We take the two tracklets. These are tracks that we're working with here, not individual images. We do have video in this setting, but the whole system works and actually in the end computes on individual images too. So we can work in video or in imagery. In this case, we take the tracklets. We have a track for person A, a track for person B. We find good frames, we compute descriptors on those frames, and then we build a support vector machine, a traditional classifier or an MLP. We tried a few different things that distinguishes between these two individuals. Right? So we're building a classifier that's going to take the visual representations of these people and highlight how they're different. And then we compute using that classifier, we compute a visual saliency map. There's a variety of methods to do this. We didn't invent any new ones here. We're just using a method from Kate Senko's group at Boston University called RISE, which is very popular. And then for each of these images, we then can project what saliency says, which parts of the image are the most distinguishing between these two individuals. So here's some more qualitative results. We have some quantitative ones following in a moment. So we can see, we look at these two pairs here. There is a logo on the shirt, and often logos on shirts are quite distinctive, right? So you can look at the marks on clothing, and they're often a good way to tell the difference between two individuals. Absolute color is often not a great indicator, as anyone who's worked in surveillance and vision knows. Color constancy is a myth, right? So the same shirt on the same individual can look very, very different in color space based on lighting conditions, viewpoint, indoors, outdoors, and so on. And so the user would look at these two and look at these two images and then look at the saliency maps and immediately see that there's a highlighting on this logo one here. And that's visually an easier case. In this case here, it's a little more subtle, which of these individuals are really the same or not. And here there's ruffles around this skirt, for example, that are highlighted here on this individual, and they're not present on that person over there. So we can confidently say they're not the same. This one is another tougher case. How are these two people different? Well, one is their footwear. Actually, this person is wearing sandals, and this one is not, and that's highlighted here, and so on. So you can go through and look at these saliency maps, and you get a very quick visual indication, particularly in a real-time setting, that this individual is not the same. So to quantify this, we looked at typical visual saliency measures for measuring how well the algorithm highlighted areas that really do matter to the algorithm's classification decision. In this case, it's just this binary classifier distinguishing between individuals. I won't go in this in detail, but there's simple ways to black out the pixels or gray out the pixels that correspond to the most salient regions and then run the classifier and see how decisions degrade over time. You can do this in insertion deletion sense. You get these ROC curves, and then you measure the area under those curves. And then we looked at a few different baselines for this. We looked at some backbones to do the appearance representation of individuals. 3 different ones that had done well on person re-ID benchmarks in the past. These are the, here in this column called rank 1 are the results on re-ID on the Mars data set. And then here are our results on the saliency problem, doing this insertion deletion metric from the RISE paper by the Boston University group. And random is 0.5. We did a baseline of random over here, looking at we didn't have good labeling between the 2 individuals, just as a sanity check. And we get above random here, not a ton, 5 or 7% above random on these deletion marks and insertion marks here. But that does show that the doppelganger saliency is picking out those key bits. Remember, these individuals are very similar on purpose. That's why they're doppelgangers. So it's actually difficult, and we don't expect a ton of the image to be different. So about 3 or 5% of difference in the image is pretty standard according to these metrics. We've encoded this in an open source toolkit. You're welcome to, it's in the paper. You can go here and try all these methods. DARPA funded us to create the outcomes of the XAI program, which is a 4-year DARPA program that developed some of this work into an open source toolkit that incorporates saliency methods. So we'd like to continue this work and looking in particular in temporal coherence of saliency, which isn't done very much. There's a bit of work in that, which is very nice. And all this can work for other fine-grained visual recognition tasks. There's an entire workshop on this yesterday, a lot of wildlife focused applications, which we do. Again, many thanks to DARPA for funding this. Questions?
Great work. I was wondering how have you looked at using some of the explainability aspects in this process, AI explainability?
The question was, have we looked at using any AI explainability toolkits for this process? The answer is yes, we've incorporated some existing implementations of saliency algorithms in this here. There are a couple other toolkits, I think maybe one from IBM that does saliency as well. We have looked at doing that not on this effort particularly, but in the effort that funded the saliency toolkit package here. There's pros and cons. We looked at some of those algorithms. This one, or the toolkit that we built, has a very permissive open source license and packages up a whole bunch of different XAI methods, not just saliency, but for autonomy and some other things as well.
I guess maybe if I could follow up on the performance chart you were saying you conducted. Did we see a significant improvement, or is just that we are getting on the catching few of the very distinguishable things?
Question is, do we see a significant improvement? It's hard to know what significant improvement is. So I think the right way to evaluate this, which we didn't have the scope to do, unfortunately, is to say, does the user do a better job with saliency? Because saliency is really a help to the user, right? It's intended to be looked at by a human to say, now I can see that these doppelgangers exist, these 2 people are really there and they're different, as opposed to the algorithm making a mistake and saying these 2 people are really one individual. So in principle, the user should be able to do his job better and faster with this system. So we didn't have the scope, unfortunately, in real-time mechanism and all of that to do a user study, which I think would be the right way to go. What this measures is the percentage of the image that saliency picked out that's salient to the decision. Right? So it's kind of upper bounded in a way, right? If only 10% of the image really is different between these 2, then one would expect these measures to be at most like 10% different. It's not quite that direct mapping, but that's essentially the take on this particular measure. So it's hard to say what a great score would be, but I'd be surprised if we ever got a score above like 0.6 or below 0.4 on these measures. Okay, thank you very much.
Just a second, maybe is there any question online?
What was the question?
Since we need,
All right. We had a question in the chat.
Since you need to train a binary classifier for each pair of doppelgangers in application, is this a concern in terms of runtime?
Right. This question is there an issue in training the classifier in runtime? The answer is actually no, because support vector machines are super fast. So And we're only training this on clips from each of these individuals. We can use multiple tracks or the individual tracks. We have a couple of hundred training chips. The feature vectors computation there is probably the most expensive step versus training the classifier. So training the support vector machine takes a fraction of a second actually on this data. But we do have to compute those feature vectors by running each of those chips through a deep network, a backbone network to get that descriptor. That's what takes actually most of the time as opposed to building the classifier. But it runs, it takes about, I think, a couple seconds to do the entire computation on normal sized chips, maybe 5 seconds at most, something like that, using a GPU in the background. So if you had to make a decision in like a second or two, it would definitely be a problem. You know, there's certainly potential lag there. And if you're using a lot of data on each individual, it could take a lot longer. But typically it's like a few seconds. So it does work for most applications. Good question.
Thank you. Okay, thank you. Let's move to the next paper. The title of the paper is Epistemic Uncertainty, Weighted Loss for Visual Bias Mitigation.
Hi.
Hi.
Can you hear me? Okay, I'll share my screen. Is that okay?
Yes.
Okay. Hi, so I'm presenting our paper on epistemic uncertainty weighted loss for bias mitigation, visual bias mitigation. So most modern intelligent vision systems learn from large amounts of data. And even with an ideal sampling procedure, there's still very likely to be bias in the data because of societal bias or bias that exists historically and in the real world. So our focus is looking at models that are learn bias because they learn from data. Further, we're looking at vision. So we're looking at very complex high-dimensional data where they're feature-rich. And it's very difficult to comprehensively identify and label all the biases that might be present in the data. So ideally, given this real-life scenario of bias in our data, we want to firstly learn a fairer model. And secondly, we would like to do so without needing to be having a complete understanding of all the sources of bias in the data. We can broadly focus on kind of two categories of bias here, just to narrow down our focus. And the first is a minority group bias. This is when a subgroup of the data has a particular attribute or combination of attributes which are relatively uncommon compared to the rest of the data set. And that makes the model less likely to predict correctly for these samples. Secondly, we can look at sensitive, or it's sometimes also known as protected attribute bias, where a sensitive attribute is one which should not be used by the model to learn a target task, but which provides an unwanted shortcut or spurious feature which can easily be learned and results in an unfair model. We would like to use epistemic uncertainties. And in contrast to aleatoric uncertainty, epistemic uncertainties are model, not data uncertainties. So they arise from the model's lack in knowledge, which is usually caused by missing data. It can be reduced given more data. In a theoretical world with an infinite amount of data, the epistemic uncertainty would go to 0. There's different ways we can approximate these uncertainties, but one way is using a probabilistic model or a Bayesian neural network. In this case, we use a cyclical stochastic gradient MCMC formulation to approximate our posterior. The Bayesian paradigm gives us the framework to train an uncertainty-aware network. So given a network with a posterior P of theta, we can compute the network's prediction for any given sample x of I using Monte Carlo sampling from that posterior. This gives us an approximation of the predictive mean. We can also use this sampling to approximate the corresponding model uncertainty associated with that input. Finally, what we propose is using those uncertainties for each training sample to sample-wise weight our loss function during training. In this case, kappa is a tunable parameter, which we use to scale the weighting. A larger kappa penalizes the model more for high uncertainty samples, whereas a kappa equal to 1 sets all the samples equally important during training. We test our method first on a visual bias benchmark dataset introduced in Wang in the 2020 CVPR paper. In this dataset, it's a skewed dataset. So for half of the classes, so 5 out of the 10 classes, 5% of the images are converted to grayscale. And for the remaining 5%, 95% of the images are converted to grayscale. While the data is balanced 50-50 across the whole dataset with respect to color, the model can easily be tempted to learn a shortcut correlation of color or not color for each specific class. So we find that our method shows debiasing potential. It's key to note that only these two bottom methods, in addition to the baseline, do not use any knowledge of the bias in order to mitigate. So all these other methods explicitly use information of the bias in order to mitigate the bias in the model. We can also formulate a second version of this benchmark dataset, which we call sci-fi minority, where we simply set 5% of all samples across all classes to grayscale. And also in this dataset, we find that our method results in a fairer model. We can further test the method on a face detection problem. So this is no face detection using celeb A as a training set. And this random selection of images from the training set shows the relative lack of diversity in the training set. We can test the model on Fairface, which is a large data set with gender, race, and age annotations, and it's balanced across 7 race groups and 9 age subgroups. And we find that our method results in an increase in true positive rates across all the minority subgroups. In addition, we can also look at our training data and inspect which celeb A images are associated with high model uncertainties during training. We find that the faces with low uncertainties tend to be well lit, are facing forward with hair cleanly framed face, primarily lighter skinned people with few accessories which might obscure the face. Whereas faces with high uncertainties in the training set are more likely to be subject to discrimination, not just because of the reasons that the gender and race other annotations that we have in the test set, but also because due to variance in lighting, in pose, coloring, and obscuring objects and accessories, in addition to other reasons. So a bias-informed method, which uses the knowledge of the bias to mitigate, could strongly mitigate bias, outperform my method, very likely, assuming that those ground truth labels were available. But in many scenarios, it's unlikely to have a complete access to the metadata, which identifies all the sources of unfairness in a data set. So in conclusion, we presented a method of leveraging epistemic uncertainties during training with potential to mitigate the bias without needing to know any sources of bias in the data. And currently we're doing further work to explore in what kind of scenarios is it more or least effective, and are there potential scenarios in which it could be harmful and our method could even potentially amplify the bias instead of help. Thank you.
Yeah, thank you for the talk. Is there any question? Any questions?
Hey, can you hear me?
Yes.
Thanks for the talk. Just wonder, could you please give an example of like how the biases from a source training data exactly?
I'm so sorry, I lost you. And give an example of how the bias can, what was the rest of it question?
Yeah, like qualitative example, like how, what kind of biases from the source training that like the model?
So the question is like what kind of bias from the source data is a more problem?
Sorry, what kind of bias from the source?
Yeah, for this specific space data set.
So it's like gender, I think that gender, race, or what kind of exact bias is there, which is a more problematic.
Okay, yeah, so in the face detection data set, for the training set, there were no ground truth annotations in which were related to the bias. However, in the test set, which was fair faces, there were age and gender and race annotations, which we used to do the evaluation. But by looking at the uncertainties and ranking them over the training set, we could also identify qualitatively, we could identify different sources of bias in the data set that you would not usually have ground truth annotations for, such as the variance in the pose and the lighting and things like that.
Okay, I think this method is kind of like not the bias for this method. Thank you so much.
Yeah,
Thank
so sorry, I still couldn't hear it super clear. I hope that responded. Yeah.
Is there any other question? Is there any question online? Seems like there is no more questions left. So thank you for the presenting.
Thank
So
you.
now, yeah, thank you. So now we have a lunch break, and I think we will meet around 1:30. Thank you everyone.
Oh, I'm sorry. I don't know what's going on. Okay.
Good afternoon. I hope you all had a great lunch. Welcome back to the afternoon session. We are delighted to have Sri Jayan from Stanford this afternoon to kick off the afternoon session. And yes, I was just reading through her bio. It's kind of very impressive. We are glad to have her. She is one of the KPMG students. I guess people doesn't need any introduction to this community. So, and she is right now at Stanford. She is also an associate director for the data science system.
Yes, AI in medical imaging.
And also, she works on the medical application of AI and that's a lab called model. So she is going to talk to us today about the medical efficient adaptation from benchmark looking forward to your talk.
Thank you very much for the introduction, and it's a pleasure to be here today. So just to start, we've seen a lot of progress in large-scale benchmark data sets and models for rich computer vision tasks, ranging from segmentation to videos to also human pose estimation. But despite this, it still remains a significant challenge to effectively perform these tasks in the long tail of real-world application domains that very often will actually care about. So for example, in many cases, we have still suboptimal requirements for learning about new concepts. Even with semi-supervised learning, for example, we still have to collect new label data for new concepts that can often be not very practical. And on the other hand, sometimes when we try to extend these models to work in new domains, we also get suboptimal performance. And so this shows an example of human mesh recovery applied to some of the long tail domains in actual applications that we've worked with. For example, looking at studying psychology videos and parent-child interactions, or sports gymnastics videos, and you can see that there's still suboptimal performance in these cases. So today I'd like to talk about some of our ongoing work on developing label-efficient adaptation methods from large computer vision benchmark data sets to these long-tail domains. I'll talk about two works, one for unsupervised biomedical instance segmentation, and then the second is for domain adaptive human mesh recovery. Okay, so first starting with the unsupervised instance segmentation. So this is something that is very much desired for a lot of biomedical applications for a couple reasons. First, it's often particularly impractical and challenging to collect label data in these domains. And then second of all, in many cases, we actually don't know yet a lot about the actual objects that we wish to be able to segment, and we're actually trying to annotate these to be able to study different new biological objects and structures. And so in this case, the unsupervised task becomes even more relevant. And so in order to address this problem, there's been existing works trying to tackle domain adaptation methods for being able to perform unsupervised segmentation in new domains. However, these existing works have still typically bridged relatively small domain shifts. And so you can see an example here where it's different domains, but we still have very common structure and shared objects between them. And so many of these works don't actually work so well when we have tasks for domains where we actually don't have labeled data in a similar domain. And so in our work, one of the actual use cases we're trying to tackle is being able to extend segmentation to be tackling many sorts of new or less explored types of biomedical images. And so we need methods that are able to work in these contexts. And so one of the hypotheses that's driving some of our work is the questions of, does there exist some general notion of objectness that can be transferred across even very different domains? And then can we bridge these large domain shifts with simple inductive biases? So this is a direction that we explored in our work on domain adaptive region-based CNNs, or DAR-CNN. That was work together with Joy Xu and Hua Chu. And so in this case, what we're hoping to leverage is where we actually do have large-scale benchmark data sets for segmentation. So COCO is a great example of this. We would like to be able to leverage these and then be able to tackle the large domain shift between the common objects in these data sets and biological objects. And so the DAR-CNN model works as follows. We actually have a two-stage model that performs first feature-level adaptation, followed by image-level pseudo-labeling. And there's been some very interesting existing work in domain adaptation that's been primarily based on sort of image-based adaptation and GAN types of models, but these don't work well when we have these huge domain shifts going from data sets like COCO to biological images. And so, so we start here, therefore, in this case, first with feature level adaptation, where here you can see the source data and target data, XS and XT. And here, we'll take the data from these domains and utilize the masked RCNN segmentation architecture for instance segmentation. But what we'll do is take the encoder and actually split it into two encoders using a domain separation module. And so one part in green here is this common encoder that's shared between the source and the target. And then the second component is the sort of private encoders that are specific to each domain. And so given these, what we can do is to enforce these losses that encourage similarity between the representations and features that are output by through the common encoder for both of these domains. And so we have a similarity loss here. And then simultaneously, we can also encourage a difference loss, the orthogonality constraint between the common the features that are output from the common encoder and from the private encoder for each of these modalities. And one thing to note here is that we do this, you can see here on the diagram on the upper right, on just a portion of these domain invariant and domain specific spaces, just so we have a little bit more flexibility here. So now, given that, for the source branch, we can actually supervise this using standard ground truth because we do have this, right? So for example, for COCO, but we take the features from the common encoder and use this for the region proposal network. And so that encourages these common features to encode notions that are useful for objectness. And then for the target branch, here we don't have labeled data. And so these we self-supervise using a representation consistency loss that's based on an assumption that we can make in biomedical images often, which is that we have a homogeneous background for the bounding box regions. And so in this case, what we do is we try to encourage some background consistency per image across the regions in this image. And use that to self-supervise the target branch. So given this, we basically use these losses to encourage the common encoder to have features that encode notions of objectness, and we sort of transfer this from the source to the target domain. But the feature level adaptation alone, it still gives relatively coarse and less refined predictions. And so given this, we then utilize the second stage of image level pseudo labeling, where here we take the high confidence predictions from the target branch and use this as pseudo labeling for augmented versions of images from the target domain. So this is the DAR-CNN model, and we evaluated this on a variety of diverse biomedical data sets, spanning histopathology, fluorescence microscopy, cryo-ET, and magnetic resonance imaging. So here you can see some of the qualitative results across these data sets, and in particular, the unsupervised instance segmentations that we're able to obtain across these. And then in terms of the qualitative results, we evaluated in two different contexts. One is trying to directly compare with existing work on still relatively small domain shifts. And so this is an example adapting from fluorescence microscopy to histopathology. In this case, what you can see is that our model is able to perform comparably to a lot of previous work that's designed specifically for these small domain shifts and for these specific tasks. The main one we don't outperform here is one that's Liu et al. Using a very nuclei specific in painting, and so it cannot be generalized to other concepts. And more importantly, using our model, but now trying to adapt from the COCO data set, so not using any of the labels from the more similar BBC data set, we're still able to achieve a very strong performance in this case. So the kind of more significant evaluation of our method is now looking at adaptation to data sets with very large domain shift. And so in these cases, many of these prior works, some of them don't apply anymore because they were very domain specific. And the ones that we can use here oftentimes are not working very well. And so here, our method was able to show a significantly improved performance on a wide range of biomedical data sets. And then finally, I'll show here just one example of sort of a real world use case in which we're using these methods in some of our ongoing work in collaboration with the Stanford SLAC Center, SLAC Laboratory, which captures a lot of these very high resolution images of cells and different organelles and structures within cells. And so here we have all these images of cells in healthy and diseased states, and we'd like to be able to study a lot of these structures, many of which we actually don't know much about. And so this is a case where it's difficult to actually collect annotated data sets. And so in this case, you can see sort of applying this method to be able to extract a lot of these region proposals and masks of features of interest here. And then we can then subsequently cluster and study these in the context of these images. Okay, so this is some of our work on biomedical instance segmentation. And then in the second part of this talk, I will also briefly mention some of our work on domain adaptive human mesh recovery. So this is the task where we have image as input, and our goal is to reconstruct the 3D human mesh that you can see here. And so there's still quite significant challenges in having these methods work well in sort of diverse in the wild settings. And in particular, it's quite difficult to collect annotated data, annotated 3D data in these settings. So a lot of the source data sets are still in relatively more constrained settings, but we'd like to be able to apply these on a wide range of very diverse data. And so one typical approach for trying to improve generalizability in these settings is joint training with 2D in the wild data sets. So in this case, we have the data sets on top here, a little bit more constrained, but that do have paired 3D ground truth. And in the bottom, we have in the wild images that have just 2D ground truth. And so a common approach is to use standard methods for trying to regress the pose, the shape and body shape and the camera parameters. And then from here, we can obtain the 3D estimation. And then for data that we have 3D ground truth for, we can train with a 3D loss. And then for data where we only have 2D ground truth, then we can use a 2D reprojection and loss here. So this is a typical approach, but it still has limitations. And so you can see that this works reasonably on some of the benchmark data sets that we have here, like 3DPW, but on some of the more challenging domains that I showed, Seedlings is a data set of parent-child interactions in psychology, and on the right is showing a gymnastics video. It still doesn't work very well in these cases. So one line of work to try and address this has been generating synthetic data sets. And so you can see some examples of this here. But there's still some limitations of this approach. First of all, the poses that you might generate in the synthetic data sets still might not contribute to the target distribution that we're interested in, especially given the long tail of target domains that we may have. And then also trying to render and generate this synthetic data and these 3D scenes can also be time consuming and expensive. And so the approach that we introduce here is to instead adaptively generate synthetic images that are from the target distribution on the fly during training. So this is work that's together with Jen Wang, Jackson Wang, as well as Angju Kanazawa. And so in this work, our goal is to develop a domain adaptive 3D pose augmentation method, which we call DAPA, to perform a better human mesh recovery for in the wild data. And so in particular, in our method, we first given an image from the target distribution. We use a standard regression network to be able to output simple body model parameters, the body shape, the pose, and camera parameters. And then from here, we can take the predicted pose here and then augment it in a vPoser latent space. And so a vPoser is a VAE-based prior that's trained on a lot of human poses. And so if we map our estimated pose into this the latent space from here, we'll typically get a pose that is in some of the more less likely regions of that latent space, right? Because we're dealing with a challenging domain. And so what we can do is take that latent representation and perturb it a bit, and we'll perturb it a little bit farther from the more canonical pose regions. And then given this perturbed latent representation, then decode this into this, this pose data gen here. And then now given this, perturbed pose, we can then actually render this using learned textures. And so we have a texture model that's trained on source data sets. And so we can render this and place that generated pose textured model back into background images that are from the target domain. And so what this gives us is that for any given input image from our target domain, we can sort of augment and generate a version that you can see down here, which has an augmented and synthesized pose. So now we can actually train with both the real as well as the synthetic images, where for the real images, we have, just in this case, typically either a 2D ground truth or a noisy 2D ground truth from off-the-shelf pose, 2D pose detectors. And so for the real images, we supervise this with all that we have. But then for the synthetic generated images, now in this case, since we generated these, we have the ground truth pose and body shape and parameters. And so we can have a stronger 3D supervision on all of these. And so our overall loss is a combination of the losses on the real images as well as the synthetic images. And so kind of what we're doing over time is that at the beginning of training, we start with predicted meshes that are maybe not too accurate. And they're also from a different distribution from the actual ground truth that is unknown in the target domain. And then over time, as we are training and generating these synthetic images, we gradually improve our predictions through the help of the synthetic images, then also sort of map to better and closer regions of the latent space that's closer to the target distribution, generate more synthetic data there, and kind of gradually bring the predicted distribution closer to the actual distribution in the target domain. So these are some examples of some of the synthetic data that's generated from our method in the target domain across these couple of challenging situations. And then we evaluated this method quantitatively, and what we saw was that we're able to get strong performance on the 3D PW data sets that are benchmark data sets in computer vision. But as I showed earlier, one example of this, this is not kind of where the biggest need for these methods are. And so we also demonstrated results on the seedlings data set, and that's this data set of parent-child interactions in psychology, which is actually one of the data sets that we work with in our ongoing work on trying to study sort of human interactions and behavior in these videos. And so here on this data set, using this method, we're able to get a pretty significant improvement compared to previous state of the art. Here are some more qualitative examples on the 3D PW data set. And then here on the more challenging seedlings data set. And so you can see how the outputs from our model in blue is able to fix a lot of the types of mistakes that we see from previous state of the art, like spin and pink. Okay, so in today's talk, I've described two of our ongoing works on one looking at unsupervised biomedical instance segmentation, and then secondly in domain adaptive human mesh recovery. And so with that, I'd like to thank the members of my group that have contributed to a lot of this work, and I would be happy to take any questions.
Thanks a lot for your talk. So I have there are kinds of methods and also the image. So I'm wondering, your degree where you have now or
Yeah, so I think there's been works that have looked at both, and so I think a lot of the image level methods have been working very well for more closer domain shifts, and so I think that's gotten a lot of attention. There's also been some, I think, joint adaptation works as well, but they generally have not been able to work well for these sorts of very large domain shifts like we have in the biomedical, these biomedical images. And so here, we try to use the combination of the feature adaptation to do kind of this a little rougher but like large shifts in these features, and then refine it at the image level.
For the second work, after you do the image level application, do you still use the feature level or image level?
Oh, so we're actually not able to use the image level to start with, because if you just try to do pseudo labeling to start, the initial model is too bad, and so what we find is that the pseudo labeling is kind of garbage. So that's why we need to do the feature level first to get kind of reasonable pseudo labels that we can then use.
Thank you so much for that. Any other questions? I have a question. So I see that I suppose you have to make sure that SMPL label for this otherwise.
So we do need to, we use this kind of trained texture model, and I don't know if you can see here, it's let's see, it's not perfect, right? So if you look here, that there's still, you can see that it's not a perfect texture here, but what we find is essentially that it's kind of good enough to be able to help provide useful augmentation in this case.
Same kind of artifact when you try to render and things like with different poses, shape parameters, there are some parts of the artifacts.
Yeah, we do see some. So you can see here, actually, this the second column is the synthetic images, and if you look at them, you do see some of these artifacts here. So I don't have like a generals of kind of where what are all the different types of artifacts that we see, but there are some that you can see here.
Okay, so basically it's going to be a trade-off kind of how much we automate synthetic data generation process and kind of that would spend on the
yes.
Right.
Yeah. Uh-huh. Yeah, so for the evaluation purposes of this model, we basically curated a data set of the adults labels, and we evaluated there. But in our actual work, we also look at the infants, and so we use the infant body model for that, and we have we're also doing some quantitative evaluation there. It's not part of this work, but the infants in this case are actually still quite difficult. As you can see, there's a lot of infants even in parent labs and so on. So so that's still, I would say, a work in progress.
there are no more questions. Let's thank the speaker. Thank you. Okay. Great. So the next speaker is Lawrence Vandermeyer from Facebook AI Research Lab. Lawrence, could you please turn on your audio, the speaker? Yeah.
Yes.
You are able to hear us, right?
I can hear you loud and clear.
All right, very good. Yeah, I guess I wanted to double check before I introduced you.
Sure.
Yeah, I guess as I just said, Lawrence is a director at FAIR, and I guess we all know his work on TSNE. That's the fame that he comes from, I guess. But he also, before joining FAIR, he was a faculty in the Delft Institute of Technology as well, Delft University of Technology. So let's welcome him to give his talk today on the systematic study of bias amplification. All yours, Lawrence.
Cool. Thank you so much. Thank you so much for the kind introduction. And first of all, my apologies for not being there with you in person today. My wife and I just had a baby a couple of weeks ago, and so I have very important diaper changing duties that prevent me from coming to New Orleans. But I'm really happy to still be with you virtually. In this talk, I'm going to talk about some recent work that we did with Melissa Hall, Laura Gustafson, and Aaron Adcock, where we looked at bias amplification and sort of tried to understand the effect of bias amplification in computer vision models or machine learning more generally a little bit better. So you know, just to sort of get us started, right? Like on a high level, image recognition has made tremendous progress over the years. Here's a plot from Papers with Code tracking the top one recognition accuracy on ImageNet over the past 10 or so 11 years, I guess. Right, and you see that sort of as a community, we've made incredible advances in terms of the accuracy of our recognition models, right? Like going from 50% in 2011 to like over 90% accuracy on ImageNet today. And so, like, if you look at this, if you don't look too carefully, then it's easy to sort of draw the conclusion that that recognition works, right? You can throw an image at a recognition model and it will correctly predict what's on the image, whether it's toiletry or spices or toothpaste. And in our team, what we noticed already a couple of years ago is that this isn't quite true. That if you start sort of playing around a little bit and look a little bit deeper, then it's easy to find examples like this where recognition actually is not working so well. For example, because objects look differently in different countries, or because they appear out of context. And so a couple of years ago, we did a study where we looked at the accuracy of cloud vision systems taken on images taken from different countries. And so what we noticed is that there are large disparities between in the accuracy of those vision systems between different countries. Essentially, if you're in North America or in Europe, these systems probably work better for you than if you're based in India or Southeast Asia or Africa or certain countries in South America. And so what's causing this? I mean, there's a lot of different things underlying this. For example, a lot of the work that we do in computer vision relies on sort of Western services like Flickr for image collection. So services that don't have a lot of users outside. And also we often rely on English as queries. And so what I'm showing here are some examples of like what happens when you search on Flickr for wedding and then for the same words translated in Hindi, as well as for spices. And what you see is that you get very different images, right? Visually very different images. And so this explains some of the effects that we're showing earlier. And I guess overall, like as a community in the past few years, increasingly we have realized that that there are many problems like this existing in our computer vision systems. Performance differences between groups being one of them, which I just showed, but there are others like gender biases or racial bias or age biases that exist in our models today. And for me, sort of one of the main things that I learned over the past couple of years is that these things are not just data problems, but they go deeper than that. And maybe one of the papers that really illuminated this fact was this paper that appeared in the NLP community a couple of years ago by Jiu Zhao and others, where what they found was that if they trained models on biased data, that the trained models would further amplify the bias in their text prediction. And so this is what is called bias amplification. So a little bit more structure. What do we mean by bias amplification? Basically, a model that amplifies bias makes certain predictions at a higher rate for some groups than is to be expected based on the statistics of the training data. In the training data, there may exist some bias that a certain class is more often predicted for a certain group. But what models that amplify bias do is they predict that class even more often for images or for examples that correspond to that group. And so this effect has been observed in a couple of papers in the NLP community, more recently also in the vision community. But at least for me, like I don't understand it very well yet, right? Like I come from a machine learning background, and so sort of my initial intuition would be that machine learning models try to model the training distribution, and so this shouldn't happen, but clearly it does, right? And so what we try to do in this work is we try to sort of get a little bit more understanding of when bias amplification occurs and why. And so in order to do this, we did a study in a more synthetic setting, because what we wanted to do in order to do this study, in order to study bias amplification very systematically, is we wanted to have sort of very tight control of the correlation between classes, the things we want to recognize, and groups, so the things that classes may be correlated with if there's bias in the data, and ideally that we want our class predictions to be independent of. And so the way we did that in this study is by using image inversion as an indicator for group membership. So we're basically going to say there are two groups. There's the group of inverted images, and there's the group of non-inverted images. And the reason we choose image inversion as a way of implementing group membership is that it doesn't introduce any sort of new visual features. It hardly alters the class prediction, but it's still easy to recognize. I'm showing some examples here from CFAR images and their inverted counterparts, right? Like you can easily recognize which one are which images are inverted, so which group are you talking about, but the visual content didn't change, right? And so like for a model, it should be really trivial to recognize whether, I guess the left image is a cow or something like that, whether it's a cow independent of whether or not the image is inverted. And so now what we can do with this is we can have very tight control of the bias in the training data. And we do this by inverting images that correspond to the positive class, if we're in a binary setting, with probability half minus epsilon. And we invert negative images, so images that correspond to the negative class, with probability half plus epsilon. And this gives us a bias of 2 epsilon in the training set, right? So positive images are 2 epsilon less likely to be inverted than negative images, right? And so this is an example of a synthetic bias. And what we're going to do is we're basically going to measure, as we change this bias, how do models respond to this? To what extent do they amplify biases? And in order to measure this bias amplification, we adopt the definition of Angelina Wang and Olga Rusakovsky that was presented at ECCV last year, which looks like this. It looks very complicated, but it's a relatively simple measure. It's summing over all groups. So in this case, inverted versus non-inverted images and classes, so the things that we want to recognize. And it sort of contains 2 terms. The first term is basically just measuring the direction of the bias. So a group membership can have a positive or negative, can change the probability of a certain class in a, it can increase it or decrease it, right? And so what this Y is capturing is that that direction. So it's basically just a sign. And then this delta here is measuring the magnitude of the bias. So this is the thing we're mostly interested in. And the magnitude of the bias is measuring the difference between the bias in model predictions and the bias in the training data. So a probability here, the probabilities that you see here on the left is the probability of an image corresponding to a certain class, given that it corresponds to a certain group. In the model predictions, that's a little hat on the T. And on the right, you see the probability that an image corresponds to a certain class, given that it corresponds to a certain group in the training data, right? And so this is a given. This is a quantity we know, at least in our synthetic setup. And so what the bias amplification is measuring is basically just the difference between these 2, right? Like, is the model more likely to predict a certain class for a certain group than should be expected based on the statistics in the training data? All right, so we started doing experiments using this measure and using the experimental setup that I described in the previous slides. And the first question we asked is, does bias amplification, does it vary with bias in the training set? So what we did in these experiments is we varied the amount of bias in the training set by changing this value epsilon, right? So by changing the ratio of inverted versus non-inverted images between a positive and between the positive and the negative class. And we train models, we train small ResNets in this case on data sets like Fashion MNIST or CFAR, so that we can iterate relatively quickly. And we measure this bias amplification measure. So that's the green line that you see here. We repeat this, I believe, 10 times, and we show the standard deviation in bias amplification between these runs as shaded regions. And so what you see is that bias amplification in these experiments is not constant. When there's no bias in the data, then there is no bias amplification either. That kind of makes sense, I guess, right? So that's the epsilon is 0 case. When the bias is perfect, right? So this is the case when epsilon is half. So then whether or not an image is inverted is a perfect predictor of the class. In that case, it is impossible to amplify the bias, right? Because the bias is already maximized. So in the case epsilon is 0.5, you also observe 0 bias amplification. But in the values in between, that's where you see bias amplification increase. And it's sort of maximal, I guess, at a value of 0.3 or 0.4, at least in these experiments. A second question we asked is, does bias amplification vary with model capacity? So, like in computer vision these days, one of the best ways, I guess, to increase the accuracy of your recognition models is by making them larger somehow, right? By increasing the number of parameters. And so that makes this an interesting question to ask. Are larger models, do they amplify biases more or less? So what we did is in our ResNets, we varied we varied the capacity of the model in different ways by adding more layers. So that's the plot on the left. By adding more feature maps in each layer. That's the plot in the middle. And by changing the weight decay, so by changing the L2 regularization on the parameters of the ResNets, that's the plot on the right. And so what you see in all these plots is kind of the same effect, where if the model has really low capacity, so in the case of depth and width, those are the numbers on the left. In the case of weight decay, it's actually the numbers on the right, because larger weight decay means sort of less effective capacity in the model. So when the model is really small, then you see large bias amplification, which suggests that the model basically uses the group membership, so the image inversion, as a shortcut to do the class recognition. But then as the model capacity increases, the bias amplification actually decreases, and it goes to something that is close to 0 for each of these hyperparameters. But then after that, once the model starts to get over parameterized, it actually goes up again, and it kind of, I guess, starts overfitting on the group membership, and so the bias amplification starts increasing again. And so what this shows is that, or what this suggests is that there is sort of a sweet spot in terms of minimizing bias amplification, and what we also observed is that this sweet spot is different from the sweet spot that you would find if you would focus purely on model accuracy, where typically models with larger capacity have higher accuracy, and you don't see this V shape occur. Somewhat similar trends we see if we start looking at whether bias amplification varies with training set size. So that's what we do in this experiment, where we vary the proportion of the training data sets that we use to train our models. We repeat these experiments for multiple values of epsilon, so for multiple values of the training set bias. And so what we see here is that if our training set is really small, then the bias amplification is typically small, close to 0. So I guess what's happening there is that the amount of data is too small for the model to really pick up on the correlation between group and class in these experiments. But then as the amount of training data increases, the bias amplification also goes up to a certain point, and then it sort of starts slowly decaying again. And I guess our data set here was too small to see if it sort of decays all the way to 0 or not. But anyway, if you compare to a plot of, for example, the accuracy, right? So the test accuracy of those same models as a function of the proportion of the training set, what you see is that these curves are really quite different qualitatively. So I think that's an interesting observation. We also looked at what happens to bias amplification during training. People, like many of you often train convolutional networks or VITs, and so you look at these kinds of training curves, like the light green curve on the slide here, that measures accuracy as a function of the training epoch, right? So that measures how accuracy improves during training. And I'm showing these two dashed lines because those correspond to decreases in the step size in the learning rate that is used for training. So in this case, we use a relatively standard schedule where we start with a certain learning rate, and then we decay the learning rate by a factor of 10 twice after, I guess, 250 and 375 epochs. This is on CFAR 10. And so I'm sure many of you have seen this effect as well, where if you decrease the step size, then the accuracy tends to shoot up. What we show here overlaid in the dark line is the bias amplification of these same models. And so what you see is that bias amplification in the early stages of training is really high. And so what seems to be happening here is that the model sort of picks up on the easiest signal first. And the easiest signal in this case is the signal on image inversion. And so as a result, the bias amplification in the beginning is really high. And then sort of over time, it starts to decay as the model starts learning more about, like, you know, the actual visual content of the classes, and starts to more and more ignore the image inversion signal and how that's correlated to the classes. But what's also interesting to see is that around these step size changes, actually things seem to be happening to bias amplification as well. In particular, after the last step size change, you sort of see qualitatively, you seem to see an increase in bias amplifications compared to sort of the middle band of the learning rates. And so it seems that even sort of the training schedule and the learning rate schedule somehow can influence what happens to bias amplification. The last thing, and sort of maybe this was for us one of the main takeaways from this study, is that a lot of the observations that we made in these earlier experiments, those seem to suggest that that bias amplification, or how bias amplification behaves, may vary depending on how difficult it is to recognize the group or the group membership versus the class membership. Right. So in the earlier experiments, the group membership was this recognizing group membership amounted to recognizing image inversion. And so it was relatively easy compared to recognizing class membership, which involves recognizing the visual content of the image. And so what we did here was sort of one last experiment where we looked at what happens if we vary the difficulty of recognizing the group versus recognizing the class. And we did this by basically using sort of one image to represent the group, the other to represent the class, and by basically like alpha blending these two images. So that's the eta value in this plot. But without going into too much detail there, like sort of the main thing is, if you're on the left side of this plot, it's really easy to recognize the class and it's hard to recognize the group. Whereas if you're on the right side of the plot, it's easy to recognize the group for a trained model, and it's hard to recognize the class. And what you see indeed is that bias amplification varies a lot as a function of this value, and in particular, you know, bias amplification tends to be more of a problem when it's easier to recognize the group that your instance corresponds to. So to summarize, like, what do we find? So we made a couple of observations. Bias amplification may vary with bias in the data in your training sets. It may vary with many model design choices. I showed model capacity, regularization, training set size, training length, learning rate schedule. In our paper, we have a couple of more such examples. And perhaps most importantly, bias amplification varies with the difficulty of recognizing group membership as well. Now, you know, in terms of sort of future work, like, I think we're far from done. Like, our motivation for doing this study was to try and get a little bit more intuition of when and how bias amplification arises. And so that's why we studied bias amplification in this somewhat synthetic setting. But obviously, like the main sort of next thing that we'll have to do is try and understand to what extent this happens in real world data sets as well. And one limiting factor there is that there aren't really any good data sets that enable such tight control over the correlation between group and class memberships as we had in this study. But of course, like we do need to do a lot more work to understand to what extent these results extend to real world settings. I think the other thing, and that's why I'm excited about this line of work, is that even these observations, they at least sort of give some ideas on how you could try and mitigate. And some of those may be really simple, right? In computer vision, we are very used to looking at validation accuracies to make design choices, right? And so like all the design choices that we've made around our model architectures, around our training regime, training recipes, etc., they're made based on these accuracy plots. And if we had looked at bias amplification plots as we were doing our experiments, we may have actually made different choices, and that's what some of the results are already suggesting. And so this provides some paths to mitigating, right? Like even just starting to look at these measures sort of as you do experiments. I hope that's something that we can get to as a community, because it will hopefully really help us mitigate some of these problems. So with that, I'd like to thank my collaborators, Melissa, Laura, and Aaron, and I'm happy to take any questions you may have.
Any questions? Yes, go ahead. Thank you for the very interesting topic. Can you hear me? Can you hear me? Lawrence, are you able to hear the question?
Yes, I can hear it.
I wanted to ask, I don't know, simpler models show bias amplification, because convolutional neural networks are quite complicated to study. And the last topic you mentioned, when it's hard to do it, it's stronger. It kind of makes me feel like maybe it's just the patient behavior. Maybe I'm wrong, but if it's only the bias which you can make your decision on, then you will completely amplificate bias, which is base your classification based on the factor which you usually use the bias. Or am I just completely wrong?
So I'm not sure I fully got the question. I think the first part of your question was around, whether simple models also amplify biases. So I mean, I guess I don't have the full answer, right? It's like we didn't try and train linear models on CFAR, and maybe we should have. That would have been an interesting experiment. The only observation that we do have, right, is that in these plots that sort of the simplest models that we have, right? So the models with the least number of layers or the least number of feature maps, that those models do amplify bias and actually amplify it more than models that are slightly larger. And I think the reason is that in this case, for these models, it's easier to recognize the group membership, so to recognize whether an image is inverted or not, than it is to recognize the class membership. And so the model sort of has an incentive to latch on to that easy signal, right? Like machine learning models are always going to find sort of the easiest shortcuts that they can find. And so I would say, sort of based on that, like I would expect that, yes, simple models can and will amplify bias in scenarios where recognizing group membership is harder than recognizing class membership. And of course, like the last piece is a little bit of a vague statement that we'd have to qualify more. But that's sort of my current intuition based on the experiments we've done. The second part of your question was a little bit, I couldn't fully hear. I think it was sort of related to like more Bayesian approaches and I guess bias variance trade-offs. Is that accurate?
Sorry, in the second one, I'm trying to explain my question, the first question, why I think that simple models would do it. But so there's not really a question. And thank you for.
Gotcha. Thanks.
Would be interesting to how we can simple models.
Thanks a lot for the interesting talk. I think I have a lot of questions that quite related to the first one and a bit open-ended also. So, like if you consider like bias amplification in the setting, we are working with discriminant models. So it's like if instead of predicting like your y given x, we focus on say a generative setting, conditional generation, for example, where we are actually doing probability x given y. So like, do you think like one thing is like, is the issue of bias amplification as we see in discriminative setting, is it going to be sort of like even as kind of like detrimental, like serious in generative setting, and also a bit more like is sort of like if we develop more rigorous vision pipeline, for example, I think there have been some work in using GANs and so like scaling the understanding and traveling based on that. So it's like, is that like, is the issue also exist in generative models, and also like, can they will be like a potential solution if it doesn't like this? So like a bit open-ended. I'm curious, like, what do you think? Like,
Yeah, no, it's a great question. It's a super interesting question. I mean, I think qualitatively people have observed that some of the recent image generation models, you know, tend to have biases. I don't know that it means that they amplify these biases. I also don't know if there are any sort of good measurements of that. I'd have to look at the literature more closely. I think from our experiments, I wouldn't dare to make any predictions on that, in the sense that, you know, even sort of quantifying how even deciding how to measure bias amplification in image generation settings seems like an open problem, in the sense that sort of the bias amplification measure that we used here, proposed by Wong and Rusakovsky, which makes a lot of sense to me because it looks at, you know, sort of bias in prediction versus bias in training data, but it also relies on our ability to determine whether or not an image is a certain class, right? And so it's sort of, I think, fundamentally designed for recognition, and it isn't immediately clear how you would translate that into generation. So I don't know. Like I'd find it difficult to make any predictions there based on the work that we've done in this study. But I fully agree with you. It's a really interesting and important topic to look into.
Could you please comment on the impact of existing more than one factor, for example, depth and width on the bias amplification? We expect to come up with bias amplification, and additionally, could you please provide more insight on what we consider as large bias amplification values according to your?
Yeah, it's a great question. So in our experiment so far, we've only looked at we've only sort of changed one factor at a time in our experiment. So we don't fully understand how these things compound, right? So like if you make a model deeper and wider, you know, does the bias amplification compounds or not? I'm not sure. In terms of what are large bias amplification values? It's a great question. I don't fully know. Like I must admit, like even at this, even after having done this study, I don't have a really good intuition for what bias amplification, sort of what the measure means and what is good or bad. What you also see is that between data sets, so like the image inversion experiment we repeated on fashion amnist versus CFAR. And what you see is that these values vary. And I think part of the reason is that it depends on what is the accuracy that you can get with your model. So like if you have a perfect recognition model, so you have 100% recognition accuracy on your validation or test sets, then the bias amplification measure is going to be 0. And so what that means is that I'd expect that data sets that are harder, right? So where your accuracy is lower, I'd expect you to see more pronounced bias amplification values there. And so as a result, I'm not sure you can talk about sort of, hey, you know, this is a good value and this is a bad value, because I think you're probably going to have to look at bias amplification relative to accuracy on the task.
One last question from the room here.
Hi, thank you for the talk. I was very curious about your epoch-based graph where you showed that is more epochs and initial epochs. If I understand, is it like some of the it tuned to some of the easy examples? Is that what you try to say? And if it's like to a certain kind of examples, do you know that what kind of image features that they might be getting biased to? And what's your thought about like solving that? That's the first part. And second part is that something you're suggesting that we should go for more epochs in general anyway for given any data? Thank you.
Yeah, it's a great question. So I mean, like, you know, like I guess these plots don't give a full understanding of what is really happening in the learning dynamics, right? But sort of the thing to keep in mind here is, one, the training set is biased in these experiments, and two, recognizing the group is easier than recognizing the class. And so as a result, what happens is that the early on in training, what appears to be happening is that the model latches onto sort of the easiest signal, sort of the quickest signal that it can get to drive down its loss, right? To get some predictions correct. And that is, in this case, it's the group signal, right? It's the image inversion signal, because it's easier to recognize than the class signal. But then, of course, you know, like it's only a weak signal of what the class is, right? Because the correlation between group and class is not perfect, right? And so then sort of as it continues training, the model is forced to start looking more at like what is the visual content, right? Like what are the actual visual classes in these images? And so then you see the bias amplification go down over time. If you turn it around, and we have those experiments in the paper, so if you make recognizing, if you are in a setting where recognizing the group membership is really hard, but recognizing the class is relatively easy, then this effect goes away. Then you see no bias amplification early on in training. You may only sort of see it slightly go up later on in training, right? So it really depends on that trade-off, which is sort of what we try to show here. In this plot, towards the end of training, I don't fully understand what happens, right? Like I think sort of when the final step size decrease happens, I don't know. Like my best explanation is that there's some kind of overfitting happening or something like that, and which causes the model to sort of latch on to the inversion signal again, which would result in the bias amplification increasing. But I don't have a really strong intuition for why this happens or what exactly is happening. But it is a very striking observation, and it's consistent, right? So these runs are averaged, or these results are averaged over a whole series of runs, and also in different settings, like we see these same effects. And so it is interesting to see that even things like a learning rate schedule, right, or a learning rate decrease can influence what happens to bias amplification, even though initially you'd think it's sort of completely unrelated. And I guess that sort of comes back to the point of like it's not just the data that is influencing these effects, right? But it's also our modeling choices. I know it's only a partial question answer to your question, but I hope it's helpful.
Great. I guess in view of time, I think we'll move on. Thank you again, Lawrence, for taking time. I know you're busy. You don't look best here. So I guess with that, let's thank the speaker again.
Thank you.
So I think now we are to the paper from the workshop.
Any authors online? Please start sharing your screen.
Hello everyone, so you can see my screen.
Not yet. Can you try sharing again, maybe?
Yeah, sure.
Now we can see it.
Okay. So good afternoon, everyone. I am Tanveer Hussain, and today I will present about my research that is pyramidal attention for saliency detection. Salient object detection extracts meaningful contents from input images and depths by distinguishing between the background and foreground. So considering the input data, the existing SOD works are RGB and RGBD based models where we focus on RGBD SOD. The existing RGBD SOD models take RGB and depth maps as input to generate image saliency, as like we can see here in the example. Different from the existing RGBD models, our method takes single RGB image as input. Our depth model predicts the depth map associated with the RGB image, and collectively the input RGB image and the predicted depth map, so they are input to the proposed PASNet SOD model to generate saliency maps. As like we can see in the figure, we have the output saliency map. So the RGBD models are trained and tested with RGB and depth data where their practical applicability in real world environments is questionable. Furthermore, depth data sometimes affect the output performance due to the noise in the input depth maps. The hybrid models, in contrast, are trained using RGB and depth data, but the testing phase is functional without depth data dependency. So as like we can see in this table, we can observe the performance of the proposed model that is different from the existing ones, and we also achieve the state-of-the-art performance. So in this work, we present PASNet, a novel pyramidal attention and transformer-based architecture for SOD. PASNet considers a single RGB image and apply firstly features extraction from the backbone network, and then pyramidal block for encoder features refining, followed by upsampling and features fusion in the decoder. So initially the RGB input is processed using two models. Firstly, encoder module produces various level features where the initial level features are refined via the base of the pyramid. The second model generates depth maps corresponding to each input image, while the depth model's intermediate features are fused with mature RGB encoder features in later stages to enhance its features representation. The decoder progressively fuses these features and upsample them as well to to finally produce the saliency map. The encoder produces alpha, beta, gamma, and sigma. Alpha and beta are actually CNN features acquired from intermediate layers of the backbone model. Gamma and sigma are transformer features from the sequence of fused alpha, beta, and gamma. So all these features are input to the proposed pyramidal block that is composed of several multi-scale dense arterial spatial pyramid pooling and multi-headed self-attention modules. So the decoder receives alpha, beta, gamma, and sigma features, progressively concatenating from the fusion of shallower to deeper layers. After each concatenation branch, PASnet has residual channel attention block as represented by theta. Theta captures spatial and channel dependencies between pixel locations and different channels of the input feature maps. The saliency map is finally obtained by gradually upsampling the features during concatenation. So the objective function used in this work is weighted fusion of several loss functions defined for X and Y here. So X is the input image and Y is the ground truth. In the equation here, epsilon refers to the constant weights assigned to each loss function. Structural loss focuses on the global structure optimization instead of aiming at single pixels. SSIM loss helps to compute the similarity very well, and the regularization is implied to do not encounter the overfitting situation. And finally, the edge-aware loss makes clear distinction between objects using disparity gradients. And in the qualitative evaluation, so we present some of the results on challenging images. So in the first image, we have the foreground that is hidden and the proposed method produced near to ground truth results. When compared to state-of-the-art model, so we can see that we have the best results among all of them. In the next figure, we can see that the background and foreground have similar color, and also the depth map has poor object boundaries. Therefore, the depth-dependent methods produce coarse results. And when we compare them to the proposed model, so we have best results among all these methods. In the next image, so it is from NGUD 2K dataset, the objects fine details such as like the pillars, so they are correctly predicted by the proposed method. And finally, in this image, the foreground and background, they have similar color, and the depth map does not clearly identify the boundaries. Therefore, SOTA methods fail to perfectly map the saliency maps of the foreground salient objects. And in quantitative evaluation, so we compared our results with existing SOTA methods. So these are the hybrid methods, and we have best results when we compare our results on existing benchmark data sets such as DUT RGBD and NGUD 2K data sets. So here red color shows the best results and blue color shows the second best results. So we have achieved almost best results on most of the data sets. And to prove the performance of the proposed pyramidal block, so we have some detailed ablation analysis. And the ablation analysis states that the proposed pyramidal attention block reduces the error rates by an average of 4.52% on 4 famous RGB data sets. So therefore, it can be concluded that the proposed PASnet has better applicability and also SOTA results. And on top of this, we also present a new SUD perspective of generating fine saliency maps without actually acquiring the depth data during training and testing. So this is all from my side. Thank you. The codes and everything is available on the GitHub page. Thank you.
I guess maybe you can clarify on what you meant by the saliency map, or is it map mostly looking at the or generalize to other
Actually, I am having difficulty hearing the question. So if you type, I can better understand.
Yeah, maybe are you able to hear me better?
Yeah, I'm hearing you well.
Okay, so I was asking, is this saliency that you described here, is it focused purely on the 3D depth analysis, or can it be extended to other applications as well, where saliency? Like morning we saw another talk about saliency, right? So I'm just thinking whether it is applicable to other saliency.
Actually, for the time being, so the network that we proposed, so it's not specific to only this domain. So we can use the pyramidal block that is the core contribution of this paper. So that pyramidal block, so it can be used in other domains, in other dense prediction tasks like semantic segmentations, and also we can use it for depth estimation, is like we have used existing model here for the time being, but we can use this pyramidal block in other domains as well, other dense prediction tasks particularly.
Great, thank you. I guess let's move on to the next paper. You want to share your slides here, or you have it there?
I shared it.
Okay. Can you answer your screen, please?
Tanveer, can you answer?
Yeah.
Maybe.
I'll share your screen so that you can start sharing.
Stop.
Yeah, stop sharing. Just say don't share.
Yeah.
Yes, so I guess to present for a minute, I had an opportunity to talk with you in the health space. So we see a lot of fact students, for most of the time, fact students are even undergrad, doing research in the space. So please welcome.
Hi, good afternoon. My name is Emil Javid. I'm a third, now rising fourth year undergrad at Northwestern. The following is joint work with Boyne and Schiffers, Boching Gong, and Aguilas Conceptuals. We're very excited to be presenting our work MedXScan, visual explanations for medical classifiers through a generative latent space. So we can start with some motivation through a scenario. So typically in AI for medical AI pipeline, we'll train some network on some data. And then we'll feed, let's say, X-ray for COVID classification. We'll get some output. Maybe it's positive or negative. And then what we'll do is we need some sort of post hoc visualization. So what we can do here is gradient class activation mapping, or GradCam, which is a very popular method. And as we see here, it's highlighting the lungs. So it's a good sanity check. So maybe our network is looking in the right place. But what if I told you that now, if we have data from some different distribution, our accuracy drops from 99% to 35%, which has been a problem very well studied, specifically with regards to the COVID X-ray data. So the problem with GradCam, for instance, is that it wasn't very fine grained. It was just casting a very wide net. So without fine localization, it's difficult to have fine grained visualization and have confidence. Another very common visualization technique is integrated gradients. And how this works is typically we have a baseline. This should be categorized as negative. Very commonly, a black image is used. And then we have some target image. And then we'll do a pixel-wise interpolation between the baseline and target. And then we're going to feed that through our classifier, take the gradients with respect to the pixels, accumulate an average, and then we'll end up with this map here. But as we can see, it's basically just an edge detector, which it's been found through literature. Additionally, it's been found to be model agnostic as well as agnostic to labels. So problems like these drive the skepticism for deploying neural networks in real practice, specifically in the medical space where there's severe consequences. So as a bit of a teaser, with our MetaScan generator, we can reconstruct a ground truth positive image. And then due to some nice latent space properties, we can actually develop a negative realization with the generator. And we have the access to this latent space, so we can actually do some very nice visualizations that we can see at the bottom compared to baselines such as breadcom and pixel-wise integrated gradients. So for our MetaScan, which stands for Medical Explanation GAN, we incorporate a pre-trained classifier to visualize into the traditional GAN formulation. So this classifier is actually going to be providing feedback on the class to the generator, while the discriminator and generator are playing their typical adversarial game. But what's interesting here now is that typically a generator will just sample from some random noise from some Gaussian distribution. But now what we're going to do is we're actually going to encode domain knowledge of medical images. So what's very common is that there's going to be some underlying structure, and then on top of that, some overlaying class features. So for instance, it could be a brain, and then there could be a tumor overlaying somewhere there. So what we're going to be doing here is we're actually going to be having the classifier force disentanglement with the GAN. So Z1, which is going to correspond to the first part of that latent vector, is going to just encode anatomy and structure. But then Z2 is going to encode the pathology or the class according to the classifier. So what we're going to be doing here is we're actually working under the assumption that disease features aren't necessarily deterministic. So for instance, with COVID or with brain tumor, the structure of a negative image is going to be the same, but then there can be multiple manifestations of the disease. It can be all over the place. So that's why we actually use a continuous representation for the class. So if it's a negative class, we just sample all zeros. Otherwise, we draw from a spherical normal distribution. So after training, we want to now visualize, do some feature visualization. So given a real positive ground truth image, we can actually find the latent code Z1, Z2 through some optimization scheme, such as stochastic gradient descent. And now, because of these latent sampling properties, we can now just assume that Z2 equals 0 in order to reconstruct a negative realization. And at the bottom, we have an example here, and we have a difference map highlighting those changes within the law. Additionally, with access to the latent space and the latent representation for negative and positive image, we can just traverse the latent space and observe how the classifier is changing with respect to the features that are changing. And this is done by just fixing that structure latent vector Z1 and linearly interpolating to that pathology vector Z2. And I think animation is a little bit nicer to see the changing pathology. And with brain tumor, it's even more obvious. So why does this work? So the objective can be found to actually maximize a lower bound of mutual information between the class code as well as the generated image. And it's been found through various works such as InfoGAN that maximizing mutual information leads to disentangled representations. Additionally, we have this continuous class code. So rather than separating and having separate manifolds for different classes, we have this smooth representation that covers all these different representations of the pathology. And this actually lends itself to very smooth interpolation, and we'll see it actually lends itself to very nice, smooth integrated gradients later on. And at the bottom, we can see that we can fix the structure while changing the label and observing different pathology changing. So for some quantitative experiments, we start off by working with some brain MRIs and chest x-rays. And to start off, we randomly generate images with some random class codes. And we want to see if the classifier can predict the class code that we gave of the generator correctly. And as we can see, the MRI and with the X-ray, that the classifier is correctly predicting those images more so than the real images. So it seems that the classifier and the generator are in good correspondence. So the generator is seeming to learn the distribution that the classifier is learning. But it's important to note that we're not trying to find what the ground truth distribution is. We want the generator to be merely a reflection of what the classifier is seeing. So next, to validate our visualizations, what we do are counterfactual experiments, which relies on this idea of what happened if we change this. So here, what we're going to do is we're going to identify features found via the MEDX scan, as well as through GradCam perturbation, and then through those features, we're going to perturb them, and then we're going to observe how the classifier's confidence drops. So basically, if you're capturing very important features, you would expect that if you perturb them in some way, that the classifier's confidence will drop significantly. So we can see that with the MEDX scan, there's a larger drop in classifier confidence for both MRIs and X-rays, which is suggesting that the MEDX scan is finding more salient features. So here we can observe some qualitative results. So a few examples. So it's important to note that the reconstructions are fairly blurry and they're not the highest fidelity, yet they're still able to capture important disease features, and for the purpose of visualization, this suffices. So moving on, I discussed that integrated gradients before. So typically we'll use like a baseline image such as a black image and do a pixel-wise interpolation. So we have access to the latent space as well as a negative realization of the image. So naturally a negative realization would serve as a great baseline. And rather than doing a pixel-wise interpolation, we can do an interpolation in the latent space. So in order to find the degree of localization, we find the ratio of pixels that with some attribution value through the standard pixel IG versus the latent integrated gradients or LIG. And what we find is that through the latent integrated gradients, it's able to use about 1/5 the number of pixels as the standard integrated gradients. And we can see at your bottom right that it's really capturing the tumor with fine detail, whereas with integrated gradients, it's capturing a lot of these spurious edges and noise. So in summary, we've demonstrated that there's a scan framework, MEDX scan, which is very informative in visualizing medical classifiers. Additionally, latent integrated gradients is a highly informative and meaningful extension of the standard pixel integrated gradients. And we see that this method has very fine-grained visualization, as well as having a lot of explanatory power. But we also saw that the reconstructions were fairly low fidelity. So future work would be looking into generating higher fidelity images and scaling up to higher resolution images. For example, using something called pivotal tuning inversion to actually lead to a higher fidelity reconstructions. And we can see a bit of a teaser at the right where we're getting almost near perfect inversion. So thank you, and I'd like to open up the questions. Realization. Yeah, so the idea is that another way to think about it is like a counterfactual explanation. So what would this patient look like if they didn't have that tumor? What would that patient look like if they didn't have like COVID? So we're basically exploiting the domain knowledge that the underlying structure, so like the brain or the skeleton, is still going to be there, but the pathology or like the COVID features, the tumor, it can vary. Yeah, so to reconstruct the negative realization. Yeah, so when we're actually training the network, we're doing like a supervised disentanglement. So essentially, the classifier is kind of being trained along with this Z2 sampling scheme. So when we want to generate a negative image, we're always going to sample that Z2, which corresponds to pathology, to always be zeros, because the patient, we're working under the assumption that the patient will always look the same if they don't have the disease. But then If we want to give it a positive image, it would the generator create a positive image. We'll draw from this continuous distribution. Oh, question. Sorry, could you speak up? Oh yeah, that's a very good question. So there are various ways that we could perturb the image. So we just use the average of the image. The reason is that using just what might be common is using black or just white. So there's like this, there's a paper from ICLR, it's like missingness bias. So there's some bias when you're going to do some perturbation or something like that. So if we use white, white is very commonly associated with like the tumor, right? So that's going to highly bias the network towards always classifying it as positive. But then black is also very biased. So we just use the average of the image as kind of like the safest option. But in the paper, we actually discuss some other methods that we can use are some more advanced, like in painting would be a more, I guess, like a fairer way to do it, which could be some future work. Very, very good question. Thank you.
Are there any more questions?
Thank you.
Sorry. If this was locally done, right, can we change to the other presentation, the next, or give the next speaker online? Who's already available? The what's your student's name? Maybe you can. And can you start presenting your?
No, I can't start. Okay, thank you. Can you hear me?
Yeah. Now you should be able.
Can you hear me now? Is okay? Is my voice okay? It's okay. Okay, thank you. Yeah. Hello everyone. My name is Han from Virginia Tech, and I'm now a research assistant in Virginia Tech Transportation Institute. I'm glad to share our paper about the color environment skin segmentation. Most of the techniques discuss skin segmentation using color information from the images. They use the color information to distinguish the skin pixels and non-skin pixels. But color informations are influenced by many factors, such as the sunlight, the shadow, or the light of the color, or even the skin tones. When this influence happens, color information changes drastically, and thus the results in the data bias. And if the skin segmentation model can't get rid of this bias, bad results will happen. So we proposed color space augmentation to solve the problem. For a given training set, we do color space augmentation for every images, and thus the training set will be enlarged. Then we use this larger data set to train the network and get new skin segmentation model. For our experiments, we trained both FSIN and UNet using the ECU dataset. ECU dataset contains 4,000 annotated images of humans from different ages, genders, and skin tones. And the 1,600 of the images were used as a training set and the 400 as a validation set. First, we do the testing on the rest of the 2,000 images from the ECU dataset. We evaluate the performance of different skin segmentation methods on different skin tones groups. The UNet model after color augmentation gains the smallest skin tone bias, but the distribution of different skin tones in the ECU dataset is not balanced. So we also do testing on the RFW dataset. Since RFW dataset is not annotated, so we can't do the pixel-wise evaluations. We proposed a new evaluation method called the skin over face value. We use the face detector first to get the bounding box of the face area and calculate the skin over face value on the pixel level. The results here show that the models with color augmentation performs better. Besides the skin tone bias, we also test the model on the other kind of color information changes. First, we do the color information changes in the testing set from the ECU dataset. The results show that the model with color augmentation has great robustness against the changes. To verify these results, we do further experiments on the images with drastic illumination and the grayscale images. The results also show that models with color augmentation has better results. Although color space augmentation we talked today is a simple method, but it is a good way to eliminate the critical bias in data. That's all I want to share. Any questions? Hello, any questions?
Yes, it was. Are you able to hear me here?
Yes, I can hear you here.
Okay. Yes, I guess my question was, you use the Fitzpatrick score for evaluation, right?
Yes.
So, I mean, my understanding is Fitzpatrick score requires a real dermatologist to mark them. So how did you get the Fitzpatrick score?
Well, sorry, I don't get your point.
How did you evaluate? It's a dermatologist who provides the Fitzpatrick score, right?
Yes.
Did you engage with dermatologists?
No. I classify the images into different skin tones manually, just by using my eyes.
Okay, so I guess as you know, the Fitzpatrick score is supposed to be only given by a dermatologist. So maybe
Yes.
I'm sure you probably might have clarified that in the paper, but it's probably a good idea to make that clear that you, the experimenter, made these labels, not a dermatologist.
Yes, I knew that, but there may be. Yes, I think this is quite a great question, but I don't find any like better data set with human in different skin tones and annotated. So I just classify the data set into different skin tones.
Yeah, what you probably mean here is that the skin tone color that you label by yourself, not
Yes.
score. Yeah, so I guess, yeah, go ahead. Yes, I guess I was going to maybe make that comment. I was going to
Yeah, I would recommend using the ITA. I mean, Fitzpatrick is a scale for how much you can burn. But sure, for ITA, you can do it visually.
Right. So I guess you know there is a method called ITA, individual typographical angle or something like that. You look for ITA as a search term for skin level. What you are looking for is a skin label, color, ethnicity label in some sense, right? So don't call it as a Fitzpatrick score, because Fitzpatrick score has a very specific meaning in the dermatologist mind.
Mm-hmm.
Any
Yes.
other yes, if there are no other comments, I guess we can just continue, and we hope to see you back for the last session.
Sorry, I can't hear you clearly.
Yeah, no, you're good. Thank you for presenting, and we are breaking now for coffee here.
Okay, thank you. I will stop share. Thank you very much. Thanks for your patience.
Yeah.
Maybe so.
We will start in 10 minutes. Yep, sounds perfect. Okay, welcome back, everyone. Today we are very honored to have Professor Bharat Hariharan from Cornell University. He's the assistant professor in computer science. And today he's going to talk about domain knowledge for data efficiency, a story in 3 acts. Please, Professor.
All right. Hello, everyone, and hello, everyone who's watching this online. Today I'm going to talk about using domain knowledge for data efficiency. And this is going to be sort of a collation of 3 projects that explore this area and sort of various versions of this area. Okay. So as you all know, the dominant paradigm in a lot of computer vision, machine learning, is to use large labeled data sets to train recognition systems. Now, what we want to do is to train a data set, train a similarly accurate, hopefully, recognition system, but with much smaller amounts of data. Now, how can we do this? If our data set is small, if our labeled data set is small, what can we do to supplement that information? And my belief is that what we want to do is to complement this limited information that we have in the training set with some form of domain knowledge, which is often quite common in a lot of different problem domains. And so today I'm going to walk through sort of 3 different projects that we've done in our group that explore this general idea. And the projects generally go from something that's a lot more mainstream now towards something that a lot of people don't think about nowadays. So let me start. The first project is on the traditional problem of what's called few shot recognition. And this is a project that was done by my students, Lu Ming Tang and David Wertheimer. Now, the few shot learning paradigm or the problem setup looks as follows. First, we are given a large base data set where we have lots of training examples for lots of categories. Think of something like imaging. On this data set, you'll learn some representation, some feature representation, some neural networks, whatever. And then you will deploy, and once you're deployed, you'll encounter a new recognition problem where we have a small set of novel classes that you've never seen before, but with very few training examples. And the goal is to build a good classifier for this small or for this new category setup. So these novel categories that you've never seen before and for which you have very few training examples. Now, when you're working in this few shot setup where every class has very few training examples, let's say only 1 or 10, I argue that what you need is a feature representation that is both invariant and discriminative. So by discriminative, I mean that data points that belong to different classes should embed far away from each other. But discriminative features are not enough. What you need is invariance where common intra-class variations should not change the feature representation status. So for example, here is a case where we're trying to distinguish between 2 classes, the red class and the blue class. The red class, both of these are different kinds of headers. Now, this particular feature representation that I've shown here is fairly discriminative because the blue examples are usually far away from the red examples. However, it's not very invariant. And because of that, the decision boundary is going to be fairly complex. So what's going to happen is that if you only get 1 or 2 examples for each class, so let's say you imagine getting only 1 red example and 1 blue example, it's going to be fairly hard to draw a good decision boundary that separates the 2. On the other hand, if you have a feature representation that's invariant to all the common intra-class variations, then even a single example from each class suffices to draw a good decision boundary. So this suggests that you need a feature representation that's not just discriminative, but invariant. The challenge is that traditional ways of pre-training convolutional networks on classification tasks are designed to produce discriminative features, not invariant. Why is that? That's because the standard loss functions that are used for pre-training, such as cross-entropy loss for classification, only penalize networks for pushing together examples of different classes.
they do not penalize the network for spreading out the examples of a single class over features. So loss functions focus on class separation, not invariance. Usually you can get away from this a little bit by introducing data augmentation and or new metric learning strategies and so on and so forth. But empirically, these don't seem to help that much. So instead, let's try to explicitly encode the kind of invariance we need. For example, let's consider the task of species recognition. So we are interested in recognizing species of birds, for example. This is a fine-grained classification task, and it's a task where it is common for rare examples to have very few training examples. So for this task, the kind of invariance we need is force invariance. For example, these two birds are the same species, but they have very different force, and that causes their feature representations in standard convolutional network architectures to be very different. So can we actually introduce some invariance? So we are going to explore the idea of force normalization. What is force normalization? Force normalization is the idea that instead of characterizing the image as a whole, we are going to characterize the appearance of each part. So for example, this is what the eye looks like, this is what the beak looks like, and so forth. And now the advantage of doing this is that when the pose of the bird changes, the locations of these parts will move around quite a bit, but the appearance of the parts won't change. So if you only record the appearance of each part, then your feature representation will in general be invariant to pose transformation. This is not a new idea. This is, has been commonly done in classical techniques for fine-grained category recognition, but it's somewhat been forgotten in the deep learning era. So the appearance of parts matters, but the location doesn't matter. So how are we going to introduce this invariance explicitly into a model? So we are going to introduce an analysis by synthesis. So let's say we are given this bird here, the training image here shown in red, shown with a red boundary. So that's my training image. And I have this test image that I want to decide, does it belong to the same category or not? And the idea is that we are going to try to reconstruct effectively this test image using patches from the training image. So basically what we are going to do is we are going to have all these patches from the test image, and then we are going to try to reconstruct each patch from corresponding patches in the training. And if we succeed in doing a good reconstruction, we can be sure that we can say that, okay, maybe this test image is actually an example of the same bird. Because if we succeed in doing this reconstruction, what this means is, well, the different patches have moved around, and that's fine because the bird may be of a different pose. But the appearance of those patches is the same, which suggests that it's basically the same bird with the same body part. So obviously we don't do this with actual patches, we do this with features. And basically the idea is we use a neural network to produce feature maps for both the support images. So the support images in this case are the training images for each class and for the test image. And then we try to reconstruct the test image feature map using each class. So we try to reconstruct it using class A, class B, and class C. And this is a very simple sort of normal equation solution to try to reconstruct sort of feature maps of this query image using feature maps of the training. And basically, the test image will be classified as, will be labeled as a class, which yields the best reconstruction. So which yields the lowest reconstruction. So in green is the reconstruction which yields the lowest reconstruction error, and that's what's going to be my label. You can now take this classification pipeline and train the neural networks end to end using standard modern few-shot learning frameworks. And what you get is a dramatic improvement in performance. So this in red is our approach called feature map reconstruction networks, or FRN. I'm showing here comparisons to two other baselines that also outperform previous state-of-the-art models. So even today, this paper was released last year, and even today, as far as I know, for fine-grained species recognition, few-shot learning on fine-grained species recognition, this model continues to be state-of-the-art. And the reason for that is because we incorporated in the model precisely the invariance we need to get this to work. So that's sort of the lesson from this. It also works to some extent on non-fine-grained settings, like sort of standard ImageNet few-shot learning on ImageNet. But I should say that we never intended this, so to speak, to work for standard image recognition tasks, because post-normalization is not necessarily good invariant for general recognition. So, okay, so this is project number 1. And the lesson here that we got is that by incorporating this needed invariance explicitly in the model architecture, we can get state-of-the-art few-shot learning performance quite a bit above existing state-of-the-art, which does not incorporate any domain knowledge. But this was in this few-shot setting where you need sort of this initial pre-training with lots of training examples and so on and so forth. Let's go to a setting where we have no labels at all. Right? So let's try to tackle a problem where we are working completely unlabeled. Can we learn a recognition system with only domain knowledge and no labels? So this project is led by involved a whole cohort of people, but was led primarily by the students Yurong, Katie, and Cheng. And the idea here, the problem set up here is we are going to be focusing on 3D object detection in self-driving, right? So we have a LiDAR point cloud that we are getting from a LiDAR sensor. And what we want to do here is to detect objects. We want to detect, in particular, moving objects, because moving objects are what you need to avoid when you're driving cars. Right? Now, we want to do this using unlabeled data. Now, people have done a lot of work on unlabeled data, but usually when people think of unlabeled data, they think of unlabeled images as basically sort of images drawn sort of IID from some generic distribution. But if you actually look at unlabeled driving data, the data that you collect by driving a car around in a city, it has a very particular structure. So for example, let's say you are in Ithaca, as we all were, and we are trying to collect just unlabeled data for self-driving. What would we do? Well, we take the car out, equip it with a sensor, and just drive it around. So one day we go to work. Another day we decide to go to Target to buy some groceries. A third day we go to the school to pick up the kids. And what we find is that as we're driving around in this way, we are going over the same roads, the same intersections, day in and day out. So each location in the city, like if once I sort of drive around enough times, each location in the city, I'm actually traversing multiple times. Like I traverse it on Sunday, I traverse it on Monday, Tuesday, Wednesday, Thursday, day in and day out all year. And so our unlabeled data is actually organized in this way. And now we can ask, well, given the fact that it's organized in this way, how can we use it? So basically, the idea is we have these unlabeled LiDAR scans. We assume that we have localization, so we know where each scan was taken. And crucially, our data is structured so that each scan is associated with multiple past traversals. So now what you can do with this, or what can you do with this? What you can do with this is the following. You can, if you look at a particular, so let's say you get all these scans from the same location. Now, if you look at the set of points inside this light blue ellipse, the lighter colored ellipse, you observe that in some traversals, there are points inside the ellipse, and in some other traversals, there are no points inside the ellipse. On the other hand, if you look at the dark ellipse, there are always a lot of points inside the dark ellipse. What does that tell you? Well, that tells you that the dark ellipse probably corresponds to some static background that's never going to move. It's just fixed. On the other hand, the points in the light ellipse, whenever they are there, they correspond to some mobile object. Clearly, it was there once and not there the next time you visited it. So clearly, it's a mobile object. So just looking at this multiple traversals, you can automatically discover points that correspond to mobile objects. You can concretize this idea using a very simple concept called persistency. This is actually not something that we came up with. This is actually something that has been done by other people in the past as well, where basically what you do is for every point, so let's say you've scanned the LiDAR point cloud, right? And you've gone through this location multiple times in the past. For every 3D point, you can look up what this point looked like in past traversals. And now you can see, well, how many other 3D points did I detect in that rough location, in that rough 3D point location? How many points did I detect in past traversals? If this point is a background point, in which case it's static, it's going to be the same in every traversal, you would expect the neighborhood to look the same in all the past traversals. On the other hand, if this point corresponds to some mobile object, it's likely that the neighborhood looks different in the different traversals. So you simply look at this neighborhood across all these traversals and look at some measure of variance, like how do these neighborhoods vary across the different traversals, and that gives you a measure of persistence. So this is points colored by persistency. Red means more persistent, blue means less persistent. And if you simply pull out the ephemeral points, the points that are not persistent, and then cluster them together to form segments and draw bounding boxes based on segments, you have automatically discovered moving objects. So in black are the discovered objects, in green are the true ground truth objects. So almost all the objects you discover. Note that it's not perfect. So sometimes it discovers some false positive objects. So for example, something that wasn't, some construction happened, for example. So, you didn't expect the background to change, but it did. So it's been discovered as an object. And sometimes it misses some objects because, there's some thresholding involved in the segmentation that screws things up. But it's a very good signal. And now what you can do is you can use this initial signal, initial set of boxes, to train a 3D object detector. And once you've got 3D object detector and unlabeled data, you can pull out one of what I should consider as a side note, what I think of as a very powerful way of using unlabeled data, which is self-training. So you take your object detector, you try to detect objects in unlabeled data, filter it again using this notion of persistency to get more training data, use that to retrain your detector, and so forth. And what you get is a mobile object detector. So it doesn't tell you what object it is, it tells you it's a mobile object, but it's able to detect this at an accuracy that rivals supervised training. So without any manual annotations whatsoever, you've gotten a 3D object detector, a mobile object detector that is almost as good as supervised training. So this paper is called, the system is called Modest, and it's a paper that's going to be presented later at the conference. So till now, I've shown you, hopefully convinced you that if you think a little bit about the domain knowledge that exists in a problem setup, you can actually train accurate recognition systems with lots of, with very little labeled training data, almost recently. Now I'm going to talk a little bit about, where does this domain knowledge come from? So for many problems, so in this case, I talked about two problems where we could intuitively guess the domain knowledge needed. But for many other problems, you have to talk to an expert to understand this domain knowledge. And so now we have to ask, well, what does the interface look like for the expert who's providing this domain knowledge? Are we making it easy for them? So let's consider a use case where people go to experts for domain knowledge instead of labels, which is zero-shot learning. So in zero-shot learning, I should say this is work done by Utkarsh, who is sitting right there. And you can talk to him about this work later if you're interested. So in zero-shot learning, what you get is you are interested in building a model that takes attribute description of an object. So for example, a horse would be described as it's a brown animal with no stripes and no horns, whereas a deer would be described as it's a brown animal with no stripes, but it has horns. And just with these attribute descriptions, you are able to build a recognition system that can distinguish between these classes in image. Right? So training involves just providing attribute level descriptions, and then your model is good to go. And now intuitively, this seems like, well, all the expert needs to do is to provide these attribute descriptions. But the problem is that these attribute descriptions are very, very long, right? So zero-shot learning is not truly zero-shot because you have all these attributes that you need to provide. This is very different, though, from how experts teach not machines, but other people. So if you look at how, for example, an ornithologist would teach an amateur bird watcher, they would not give you a list of 100 attributes. That's just too difficult. If they give 100 attributes for 200 birds, they have to specify what 20,000 things. That's just not feasible. Right? That's not how they describe species. Instead, what they'll do is they will build upon your knowledge. So, for example, this is a snippet from a field guide for birds, and it describes a new species, a missile thrush, in comparison to a similar species that you've seen before, a song thrush, and says that, well, how is the missile thrush different from the song thrush? It is larger than the song thrush, and its breast has much less buff. Right? So it's specifying two key attributes that are different from a category that you already know. A very concise description. Now, you could use this interface, you could use this kind of an interface for zero-shot learning, where the expert annotator specifies all these distinct attributes to the zero-shot learner. But we found that this naive approach doesn't really work well, because what's important to an expert is not the same as what's important to a machine. You see, when experts teach humans, they're talking to someone who's very similar to them in terms of their visual perception. But machines are not similar to humans in their visual perception. So we take a different approach where the zero-shot learner, the machine itself, decides which attributes it wants. So first, the expert says that, okay, here's a new category, a tree swallow, that's similar to a previous category that I've shown you before, the cliff swallow. And then the model asks the expert for particular attributes that it thinks will help it identify the species, and uses the expert's annotations to update its representation of this new species. So this here below, this vector below shows here how the representation is being updated with each user. So this allows, what does this allow you to do? So before I do that, let me actually show the results first. What this allows you to do is that it allows you to rapidly produce a good zero-shot learning model for a particular category with only a few queries. So only with a couple of queries, you get an accuracy that's sort of as high as you would get if, or close to what you would get if you were to query for hundreds of questions. The key obviously is choosing the right question. And what we find is that one effective way to choose the right question is to look for attributes that vary a lot within that particular subtree of the class hierarchy. So for example, if the nucleus that I'm trying to recognize is an Oriole, then I should look for attributes that vary a lot among the Orioles. And those should be the ones that we query. In the paper, we explore a lot more about sort of what precise strategies you might use, and we consider 3 or 4 different strategies. But the sum total of this is that we are able to think through what is the actual work that a domain expert has to teach your model this new recognition task and to reduce that burden. So to conclude, what I've tried to show you today is a couple of things. One is that with domain knowledge, you can actually reduce the amount of labeled data needed for various recognition tasks, sometimes down to 0. But I also want to sort of point out to you that when thinking of domain knowledge, we have to also reason about where this domain knowledge is coming from. And so that requires actually sometimes going beyond existing benchmarks. And in some work that I was not able to cover today, we've also looked at zero-shot learning and shown how existing benchmarks don't actually do the right thing when it comes to getting informative annotations from the expert. With that, I'll end and I can take it.
Thank you so much, Professor. Any questions from the audience?
Yeah, it's a very good question. And I think, and I'll repeat the question just for Zoom audience succinctly. The question is, when we're talking about incorporating these domain invariances, these invariances in the recognition architecture, doesn't that depend on the particular data sets, the particular application? And that's exactly right. And my approach to this is, there's some amount of research on this that you can do in a domain agnostic or problem agnostic way. But in a problem agnostic way, you can only go so far, right? At some point, if we really want to solve this problem of data absence learning, we have to indulge with and engage with the domain. And in that case, we have to figure out exactly what invariance is, right? So the invariance I described, you're exactly right, will only work, it's especially designed to work primarily for fine-grained categorization of species, right? It's not going to work to distinguish between a car and a motorcycle because there's other invariances that are required. So you're exactly right, and my answer is we should reason with that. So yeah, that part is also true. Right now, I mean, a lot of mainstream recognition work focuses on this somewhat misleading idea of a generic benchmark, right? There are actually lots of application data sets available, right, and application problems available. And I agree that sort of working through these applications and showing sort of, oh, these kinds of things fail in these applications, that's very important. Definitely. So it's a hole in our current research. Thanks a lot. Is getting question? The question, right?
I had a question about your recently domain experts. So what's typically for this group of learning setup? I was wondering how much effort is put into establishing this channel of communication for the model, so the ability to have the model ask questions to the experts and the experts being able to communicate in a kind of language with the model back. And then beyond natural language, they definitely presented and thought about any ways to communicate some visual.
That's both are very good questions. Okay. So one thing I should say is that here, a lot of the experiments we did were somewhat in a simulated setting. Well, we did have one experiment with actual experts, but we started that experiment based on previous work that had gone into defining this attribute hierarchy, right? So that involved sort of recognition experts several years ago, like including people like Serge Bilongi and Pietro Perona and so forth, talking to ornithologists and writing down sort of or going to field guides and writing down what that hierarchy looks like, right? Even there, we found that that channel of communication was flawed. For example, the benchmarks required, or the recognition systems required sort of floating point values for attributes, which did not make sense from a communication standpoint as to how can sort of an ornithologist say what the degree of redness is. And we realized that that was primarily because the benchmark had not considered the fact that for bird species, appearance can be multimodal. So males can look different, females can look different, and sort of you have to have separate attributes for these and so on. So that's a big question, right? And the answer to that is that it's somewhat problem specific, right? So there is this groundwork that needs to be done before we can talk about any of this, where we have to sit down with the expert, define the taxonomy of, what are the distinguishing characteristics that identify these species and so forth. We have talked about, so in terms of your other question about other kinds of communication, we have explored a little bit of that. So when I talked about this post-normalization work, we had a previous paper where we looked at, well, what if the expert could provide a few annotations about where the object part is, right? So where's the beak, where's the wing, and so forth. And we did find that it was very useful. But beyond that, there is, I think it's an interesting direction in terms of sort of what and how should we communicate between the machine and the expert. Beyond sort of localization and language, I don't yet have other solutions. But that's a good thing. So it's a good question. I kind of sometimes that's the fact that this zero-shot learning also happens in this kind of a base category, zero-shot category split. So for some categories, the attributes are fully annotated, right? I think the approach itself can be adapted to the setting where you start sort of tabula rasa, so the network doesn't, the model doesn't even know what the attributes are. That's a more interesting setting, but the experiments themselves have not sort of actually. Yeah, so it's kind of interesting. It doesn't align that well, and Utkarsh can sort of, you can ask him about more. But it turns out that some attributes, so if you ask an ornithologist or if you're sort of a birder, you'll know that the important cues for recognizing birds, the most important ones are size and where it is in the world, right? Both of which are not captured when you take a close-up of the bird. So it's difficult for the model to infer those things. So if you ask an expert, they'll be like, yeah, it's a large bird, but then the network can't use it because it doesn't know how to respond. Oh.
Right. So coming up, we have another invited speaker, Chen Roy. He's a professor in the Nanyang Technological University. He's associate professor with the School of Computer Science and Engineering. So the talk he's going to give today is on the training generative adversarial network with limited data. So because it's late in Singapore at the moment, so Professor Roy pre-recorded a video. I'm going to play it right now. Make sure.
I would like to thank the organizer for inviting me to share our work in this workshop. My name is Chen Lloyd. I'm from Lab at NTU in Nanyang Technological University. So the title of my talk today is Training Generative Adversarial Networks with Limited Data. So this is based on our paper published last year in NIPS. So it's called TCV, Adaptive Pseudo Augmentation for GAN Training with Limited Data. So we know generative adversarial networks typically require a lot of data for training in order to synthesize high fidelity images. So training GANs with insufficient data tend to generate poor quality images. For example, if we only use 7% of data from FFHQ and train StyleGAN2, so this is what we get from the model. And if we train it with a data set which is small by itself, for example, this AFHQ cat 5K, the results are not satisfactory. So in general, collecting sufficient data sample for this GAN model is sometimes infeasible, especially in domains where data is originally sparse or hard to collect. In this work, what we are interested is to investigate new strategies for training GANs with limited data while preserving the quality of synthesis. So before we go into the details, here I compare the results obtained by our method called adaptive pseudo augmentation APA with that of StyleGAN2 when both models are trained with limited data. So as can be seen, the quality of images generated by APA is much higher than that of those that we obtain from the conventional StyleGAN2 when we train with limited data. The significance and difficulties of training GANs with limited data have been attracting a lot of attention recently. And many of these observations show that data insufficiency tends to cause overfitting in the discriminator, which in turn hurts the stability of training dynamics in GANs, compromising the quality of generated images. So what happens is that in GANs adversarial training, the goal of generator G is to deceive the discriminator D and maximize the probability that D makes a wrong judgment. And therefore, G keeps refining its generated samples to better deceive D over time. When the training only has access to a limited amount of data, one would observe that D turns out to be overly confident and hardly made any mistakes, causing its feedback to G become meaningless. To investigate this phenomenon further, we trained two StyleGAN2 models on FFHQ dataset, one with 70K of data, which is the full dataset, and another one with just 7,000 images, which is 10% of the data. And the phenomenon can be seen from the two plots here, which compare the snapshot of training. The settings of the two models differ only by the amount of data available to them for training. The first two lines here show the raw output digit of the first GAN model that has full access to the data. And the first one here shows the logit for the real sampled, and the other line here shows the logit over time for the fake samples. And the other two lines here show the logit for the GAN that only has access to 10% of data. So as can be observed, if we compare the two processes, so both training processes, they start smoothly, and the distributions of the discriminator output for the real and generated images overlapped at the early stage. As training progresses, the discriminator, which only has access to limited amount of data, which is 10% of data, experiences more divergent predictions, okay, compared to the GAN that has full access to the data. And the divergence show that D becomes increasingly confident in classifying real and fake samples. And at the late stage of the training, D can even judge all the input samples correctly with high confidence. And meanwhile, the evaluation FID scores, lower is better, deteriorate, consistent with the divergence of these predictions. And the phenomenon above demonstrates that how a discriminator gets overfitted quickly with limited amount of data. So how to solve this problem? So many research studies propose to apply standard data augmentation for GAN training to enrich the data set to mitigate the overfitting of discriminator. So a popular approach here is called adaptive discriminator augmentation, or in short, ADA, published in NUPS 2020. So what it does is to monitor the overfitting status of the discriminator and adaptively applies external augmentations to the real images and as well as to the generated images from the generator. So here we have the variable called P that controls the strength of augmentation. The larger the value of P, then the stronger the augmentation that one would apply to the images. And this is shown to help mitigating the overfitting of discriminator. Another approach is called a model regularization. So under the limited data setting, a paper last year proposes a regularization term to regulate the discriminator predictions using two exponential moving average variables that track the discriminator output throughout the training. And they show that by tracking the moving average of the prediction, one can reduce the variance across the mini batches and stabilizes the regularization term, which is given by RLC over here. And this regularization term, in turn, will help to mitigate the overfitting of the discriminator. So in our study, we hope to explore an alternative approach, and we call our method as adaptive pseudo augmentation APA. So this method is simple and effective. Basically, it doesn't involve any external augmentations as in ADA, or it doesn't involve any regularization terms. So in contrast with previous standard data augmentation, we exploit a more natural way of using the generated itself of the GAN to provide the augmentation, which is a more convenient way to regularize the overfitting of the discriminator. And compared to model regularization, our approach is more adaptive to fit different settings and training status without manual tuning. So this is how our method works. Given a typical GAN framework, and with just limited real data for training, APA fits the images synthesized by the generator to the limited real data, okay, into the limited real data moderately. And this fit data are presented as real instances to the discriminator. So the goal here, the goal of this pseudo discrimination or pseudo augmentation for the real data is not to enlarge the real data set, but to suppress the discriminator's confidence in distinguishing real and fake distributions. And such deceits are introduced adaptively through monitoring an overfitting heuristic lambda defined by the discriminator raw output logic. So if this lambda is high, which indicates overfitting, then you will present more fake instances as pseudo real data to deceive the D. Otherwise, if the lambda is low, then the method will automatically reduce such deceit. And specifically, the level of lambda will adaptively affect the augmentation or deception probability P throughout the training. And we note that blindly presenting the fake images as reals to D may weaken the fundamental ability of D in adversarial training. So in our approach, the disease is introduced adaptively to avoid any potential adverse effect. And to moderate the deception, we perform pseudo-augmentation by monitoring the level of overfitting. So here we apply so-called overfitting heuristic lambda that quantifies the degrees of these being overfitted. So in our study, we investigated 3 variants. The first equation here estimates the portion of real images that obtain positive logic predictions by D. And the second equation here, lambda F, estimates the portion of fake images that obtain negative logic predictions by D. And the third equation, lambda RF, indicates half of the distance between the size of the real and fake logic. So for all these heuristics, lambda equal to 0 represents the situation where we do not see any overfitting. And lambda equal to 1 means complete overfitting. And in our experiments, we use lambda R by default. And we study other 2 variants in our aberration studies. So let me show the results analysis. So here we show the effectiveness of applying APA on various data sets. In the low data regimes, so you can see that by applying APA, we can get much better results compared to the conventional STALGAN2 on this cat data set, on FFHQ, as well as anime and the COP12K, the BRITS data set, which itself only has 12,000 images. So you can see that our method basically generates more photorealistic results with less artifacts. In terms of quantitative analysis, we report the FID and deception score. FID is lower is better, and deception score higher is better. And we show that by applying APA, it helps to boost both FID and deception score in all cases, suggesting that synthesized images are with higher quality, as well as diversity on different data sets. And the figure here shows the results when we gradually reduce the number of training images from 100% to as small as 1.4% of data, from 70K of images down to 1,000 images. So I can really observe the quality drop of STALGAN2 is significant. And in contrast, the quality of GAN with APA drops more gracefully. And notably, the quality of synthesized images by APA on 5,000 of images and 7,000 of images is visually close to STALGAN2 when the model has full access to the data. And APA is visually close, yet with an order of magnitude fewer training samples. And here we further study the overfitting and convergence status of APA compared to STALGAN2 on FFHQ. So without APA, which is the original STALGAN2, we can see that the logic of real and fake diverge a lot along with the training report. And with APA, with only 10% of data, we can get very good behavior. You can see that these 2 logic curves, they basically close to each other. And this translates to a good FID scores, which is close to the original STALGAN2 with full access to data. And whereas the one without APA, you can see that FID keeps increasing. And this slide basically visualize the training convergence comparing STALGAN2 and APA. And also we plotted the FID scores over the training progresses here. So as can be seen with APA, the model behaves better and generate better quality of images. And for more details, like here we only show the StarGAN 2. If you want to know the behavior of big GAN and emission studies, you can refer to our paper. And here we compare the proposed APA with other state-of-the-art solutions for mitigating discriminators overfitting. The first row here shows the results of StarGAN 2, and you can see that the results are not satisfactory given limited of data. And this is the method proposed by a CVPR paper last year called adversarial regularization. So you can see some improvement, but the quality is still not satisfactory. And this is the ADA proposed in NeurIPS 2020. The results are much better in this case. And with our APA, we obtain comparable and sometimes even better performance if you look closely. And interestingly, our method APA can be combined with ADA and yield better results. And in terms of training costs, we compute the average training time. So StarGAN 2 basically needs around 4.7 seconds per 1,000 of images. And ADA, because it needs to perform external augmentation, so the time needed is higher. If you compare with our proposed APA, the time is lower, because what we do here is that we make use of the generated images of the generator itself rather than performing external augmentation. So the time spent in training is not much different from the original StarGAN 2. And we also attempted in the generation of higher resolution examples. We have the same conclusion. So when we use StarGAN 2 with limited data, then the results are not good. And if we apply APA, then we basically mitigate the overfitting of the discriminator and generate better images. So in summary, with negligible computational cost, you can actually use APA to achieve comparable or even better performance than other types of solution on various data sets. Yeah, and you can use as small as like 10% of the original data to train your GAN model, and that saves a lot of training times. And a good thing about APA is that it is complementary to assistive methods like the ADA or the regularization methods, and you give better performance. So you can get the code and model from this link here, and we also have our project page. And before I conclude, we also want to show you other papers that we have in the CVPR. And the first paper here is about high resolution portrait style transfer. And the paper basically also talk about how we can train a GAN for style transfer with just limited amount of data. So what is special about this model is that we only have a single model that can accept arbitrary style to perform a sampler-based style transfer. So instead of having a cartoon model, a caricature model, or anime model, we can now have a single model that accepts different styles and perform style transfer. So the model that we propose in this paper is called dual style GAN. It is based on the StarGAN 2 model, but we introduce an additional style path that accept as so-called restricted style path to accept style images that is chosen by a user to modulate the styles in the StarGAN 2 model to generate the result that we want. And there are a few advantages of this model. Can generate high resolution results, and is training data efficient. You only need to only need to collect around 100 to 200 images of a specific style, then you can train the model effectively. And you can perform a very good style transfer on color as well as structure. Here we saw some results. And this is another paper called Unsupervised Image-to-Image Translation with Generative Prior. So what we try to do here is that we want to translate an image to another domain. For example, from cat to face, from bird to dog, from face to cat. And this problem has been extensively explored in the literature. And it is hard because of you don't just transfer the global style, but you need to need to consider the geometry as well. So, and in many cases, you do have the domain-to-domain supervision. So what we want to do is how we could train a GAN model in an unsupervised manner with generative prior. And here we try to exploit the big GAN prior. So what we observe is that given the same latent code, and we can generate objects of different domains with a very high content correspondence. For example, if you use Z1 here, we can generate different species of dogs and different cats, different birds with very similar content correspondence. And we can make use of this data to train our model. And we can perform distillation of this from this big GAN and to train our model to perform multimodal translation. And we show that how we can train this model and generalize two classes beyond this missionet. And the method is called GP unit. In summary, it's a two-stage versatile unit framework, and it can discover robust content correspondences with only domain supervision, and learn adaptive multi-level correspondences merely via a generation task. And it can work on close domains, distant domains, as well as extremely distant domains. So if you're interested, you can visit our poster, and we in our lab in this CVPR we have a total of 18 papers. So you can visit this link to get the PDF, the supplementary material, and also can check our project pages. And that's all for my talk, and thank you for listening.
Thanks, the speaker. And just want to mention that Professor Lloyd will be able to join a online Q&A section at around 5:40 after the last talk. So if you have questions, you can come back around that time. Coming up next is it's a paper presentation by the authors of paper entitled "Segmenting Across Places: The Need for Fair Transfer Learning with Satellite Imagery." Are there authors here in the start sharing? Oh, okay.
Hi everyone, my name is Mel. I'm a CSPT student from New York University. It's a pleasure to have the chance to introducing our work titled "Segmenting Across Places: The Need for Fair Transfer Learning with Satellite Imagery." Thank you. So the initial motivation point is that increasing availability of high resolution satellite imagery has been boosting the quality of computer vision models in tasks closely related to human life, like land cover measurements, climate change monitoring, and because of the high cost of pixel level annotation, the concept of transfer learning has been crafted to use in this field, with which model can be adapted from a data-rich location to other locations. So in this work, we emphasize the fairness implications, and this figure can discuss a bit of the issue that there are two satellite images from urban and rural. And you can see the segmentation maps generated by the UNet model on the right side. For the urban image, the objects are well segmented. For example, the buildings represented in red, the roads in yellow, and the water in blue. But for rural image, like objects are barely detected other than water. So here is a demographic statistics of people living in urban and rural areas across the world in 2018. As you can see, the imbalanced ratio here, much less populations live in a majority rural areas. So concerns must be carefully treated of potential biases towards the minority. So in this work, we conducted fairness analysis in the context of transfer learning with satellite imagery data. Now let me quickly go through the data and methods we use. We use a public large-scale satellite imagery data called LabPA. It consists of almost 6,000 30 centimeter fish ratio satellite images from 18 districts, and there are 9 urban districts and 9 rural. There are 7 land cover classes. We used two networks, UNet and Deep V3, backboned with resonance 50. And there are 2 unsupervised domain adaptation methods for transfer learning we use. Class balanced self-training from 2018 and the instance adaptive self-training from 2020. We chose these models and methods because they obtain the best performance from the original paper of the dataset. The metrics to measure segmentation accuracy is an intersection of union. We record the IOU score on each land cover class, and the metrics for fairness evaluation are built upon it. There are standard deviation of intersection of unions across the 7 classes used to measure how variant the class level performances are. The IOU of the worst performing class, and finally the IOU of the top 2 classes and bottom 2 classes. So we implemented 3 tasks for fairness evaluation with those metrics. In the first task, images from all districts were mixed, viewed as a single domain, and model performance was tested on rural and urban images from testing sets separately. The below table shows 4 metrics of results. There are performance disparities between rural and urban groups. That rural area has higher mean IOU performance, but urban area obtains better fairness performance. Specifically, they have lower class level standard deviation and a higher score for worst performers. So like more fair. And the next 2 tasks are all about transfer. We first transfer the model across districts, and the 2 unsupervised domain adaptation methods were used to adapt the model trained on the source districts to the unseen target districts. The same set of metrics are reported in the table. First of all, it's worth noting that models have high unfairness upon transfer, no matter they use domain adaptation or not. As you can see, the difference is numbers in the columns in shades. And then look deeper to the numbers. Domain adaptation methods reduce the performance drop on the target domain, which is desired. However, like they enlarge the rural-urban gap with almost all metrics. So this has motivated us to go beyond single evaluation dimension of overall accuracy for methods. Then a similar analysis procedure goes to a different type of transfer. Transfer across rural and urban places. In this context, the fairness implications will be cross land cover objects. Again, the domain adaptation helps the transfer with a higher IOU, shown by the number in bold in the first column mean. But it's worth noticing that the two domain adaptation methods all increase class level standard deviations, which means they make performances for classes less equal. So let me get back actually. Yeah, very short takeaways here. For the three tasks, models present fairness issue from multiple axes in both single domain tasks and transfer learning tasks. For common unsupervised domain adaptations, transfer accuracy is improved, but at the cost of fairness. The performance gap between rural and urban group is enlarged, indicating the need to design new methods that transfer well for both groups. Beyond these experimental findings, we explored a bit further on the cost of fairness. We examined shifts from source domain to target domain and see if the unequal shift is the cause. So there are shifts on two levels. Raw image distribution level measured by two distances, the proxy A distance and the maximum mean discrepancy distance. And the class distribution measured by pixel count. So the observations are that shifts in certain direction of the transfer likely affect performance disparities, where each class is a different situation. Of course, more fine-grained analysis are needed for a deeper interpretation. And we also would like to take this work to disclose the issues and lead to further investigations in optimizing methods. So yeah, this would conclude my presentation. Thank you for listening and happy to take thoughts and questions.
Online.
I know. Yeah.
I had a
Yeah. Yeah, very good question. So the definition of rural urban are just manipulative. So there are also other methods to divide them, like from the average income or population density. But now we are using the definition from the government. Yeah. In the visualize the bias in the divider. Mm-hmm.
Income level also reflecting
Yeah, so high income area. We haven't started specific this type of area, but I can see it has some similarity to the urban area in the study. So they have normally have very organized the building layout or very wide and straight roads instead of narrow and curving roads from the poor area, which potentially are easier for model to detect. So that's some observation from the raw image. Yeah, I think we need more like a visualizations of the representation generated by the model to be able to tell. Yeah. Thank you. Uh-huh. Yeah, that's some goals in the future because right now this data set they are like 3 cities from the same province from China, so they are kind of similar areas. Yeah, and we build different cities and at different domains, but of course more areas from maybe outside of China, other countries or other geographical locations will be good. And yeah, I think the annotation, pixel annotations for segmentation and also the sensitive group information is the limitation. So that's the goal. Yeah, thank you. And stop sharing. Yeah.
So the next paper title is an examination of bias of facial analysis based BMI prediction model.
Hello, everybody. Can you hear me?
Yeah.
Okay. Yeah, so this is a joint work with the University of North Carolina and with Dr. Carl Richnick and with Dr. Toyla Hill. The basic aim of this work is to examine bias of facial analysis methods which are actually used for BMI prediction. So, basically, let's talk a little bit about obesity. Overweight and obesity is actually a growing epidemic around the world, and it is linked to social determinants of health. Let's say gender, race, and then your income and all that. So, which is actually one of the biggest driver of other chronic disease, right? So, actually, there is a lot of initiative being going on to develop some methods which are self-diagnostic tools. Let's say using facial images and detecting BMI so that you can actually do weight monitoring as well as management. So a lot of studies have been done. There are various data sets. Let's say from MIT, there is visual BMI data sets. From Europe, Andrea group, there's a data set called VIP attribute data set. But the basic thing is that most of these data sets consist of Caucasians and they are annotated with BMI information. The aim is to do some kind of regression so that you can estimate BMI based upon facial images. Talking about all this work being going on with advances in deep learning to detect BMI, there is also a lot of literature on bias and fairness of facial analysis method in general. So most of these studies, they're actually evaluating bias across demographic groups, which we have been talking since morning in this particular session, that the systems, they do not perform equally across various demographic groups. Let's say they perform, they outperform for males over females. They actually perform better for white-skinned people over darker skin tone people. So, however, most of these studies are on gender classification, age classification, facial recognition systems, and even age classification systems. But however, none of these studies have been performed for facial analysis based BMI prediction tools, which actually there is let's say, at least around 10 papers we have in this domain where people are actually trying to use facial images and using cutting edge computer vision based technology to detect BMI from facial images. So contribution of this work is to evaluate bias of BMI prediction tools, which are based upon facial images across African American and Caucasian males and females. And to this aim, actually we have modified the MORPH2 data set. Worth mentioning that MORPH2 is the only data set that consists of that is annotated with BMI information, and it has Caucasians as well as African Americans, males and females. And then apart from evaluation of the bias, we also wanted to understand what is the cause of this differential performance. However, talking about this data set, thanks to Dr. Karl Rishnik, who is also one of the co-authors in this work, he actually has provided us this data set. So while analyzing the data set, we found that it was overly skewed towards Black population. Right? Let's say 90% of the samples were from Black population. So however, we know that the biased data set produce biased models. So actually, we first of all, we balance this data set to make sure that it is balanced across gender, across race, and across BMI broad categories, let's say normal, overweight, and obese. For that aim, we actually used 2 in-house data sets. They were also provided by Dr. Karl Rishnik to us because he has a company and then he has so many samples, so we could use that. However, worth mentioning that this particular mob data set is actually taken in control environment. So we actually manually used images which were also in the which were of high quality with neutral expression, so that we do not actually change the distribution of the data set. We used 5 new CNN models, and actually which were used for BMI prediction, and then we evaluated the bias of this BMI prediction. So this is the mean absolute error, which actually you can see for all the 5 different models, and on an average. Before talking about this particular table, let me mention a little bit about the existing literature, which says that basically white males, they tend to outperform white females as well as Black males and females. But we saw actually little bit different trend. We saw that error was actually less for Black males in general. Right? But remember that this is a different task. Here we are actually trying to predict BMI from facial images. It is not for gender classification or some other task. We have actually jotted down these results with overall performance for Black females, and then we have actually categorized this error rate, mean absolute error for normal, overweight, and obese categories. So overall, on an average, the performance was it was higher for Black males in general. Right? So males in general outperform females, but Black males outperform all of them, and white females were the underperforming group for this particular task, which is in contrary to existing literature, as I mentioned. So, and this is the overall statistic of the table 1, which I showed you, right? The mean, max, and standard deviation. So again, the same thing, which I discussed with you. ResNet 50 performed the best, and for this particular task. And then, as I mentioned, that minimum mean absolute error was obtained for Black males and maximum for white females in this particular task. We wanted to learn that what is the cause of this particular phenomena, which we are actually observing. So we tried to even evaluate psychology-inspired geometric features. So these features have been established. This is not our own invention. There are a lot of papers which actually say that facial width to height ratio, cheek to jaw width ratio, and parameter to area ratio, they are actually correlated with BMI of a person. And we used actually 260 images. These are neutral and then images and high quality to understand why these Black males are actually outperforming this for this particular task. We annotated this with a DLIP, which actually gave us 68 landmark position of the facial images. We actually learned this, we extracted these features from facial width to height ratio, which is nothing but, so facial height is vertical distance between the most inferior point of the upper eyelid and the most superior point on the upper lid, which is actually basically this. And then the facial width, horizontal distance between the two most lateral facial points. Right? So larger, this ratio indicates a wider and a squarer face, right? Wider and squarer face means that there's more fat content on your facial images. And this is actually positive correlated to increasing BMI, right? So facial width to height ratio will increase if your BMI is more. It will be actually, it should be more for obese category in general. Another is cheek width to jaw width ratio. So cheek width to jaw width ratio is, cheek width is horizontal distance between the two most lateral facial points, and which is this, and the jaw width is width of the face at the mouth. which is this, right? Smaller ratio indicates a squarer and wider face, right? So if this ratio is smaller, it means that you have more fat content on your facial image. And then the third one is parameter to area ratio. This is actually ratio of the parameter of the lower half of the face to the area of the lower half of the face. And this also indicates wider and squarer face, right? If this ratio is high, it means that you have more fat content. So this is some of the observations, right? This actually we have obtained this information for all 260 images, which actually they were high quality so that there is no pose variation and we understand what is the cause of this phenomenon. So our results indicate that, right? So we actually have computed this for non-obese and obese category only for this particular task. And we saw that for black male, this percentage increased, that facial width to height ratio, it increased, there was much higher increase between non-obese to obese group, right? And cheek jaw to width ratio decreased for, there was much higher decrease for this particular group, that is black male. And then parameter area to this particular ratio, this is also was decreased for this particular group most, which means that from non-obese to obese black male, these metrics are very significant, right? So that is why it is actually helping our BMI prediction tool, and that is why black males are outperforming. It seems like that for this particular task, right? So key findings for our particular study is that black males, they outperform, white females underperform, males outperform on an average over females, which is actually along with the state of the art, which states that males are actually outperforming females. Obese black males had wider, squarer, and rounder face compared to non-obese black males. Actually, for this particular subgroup between non-obese to obese, we saw this much difference on the facial, these matrix. That is why, which is actually aiding this BMI prediction tools, right? However, for white females, we did not see much change in the facial images from non-obese to obese group using these particular matrix. That is why it was not helping BMI tools to predict weight from facial images. Having said that, facial images are not enough to predict BMI. We need other measures as well, such as waist circumference and many other attributes. But however, aligning with the current literature, which is actually trying to see how much potential facial images have to predict BMI. One shortcoming of this study is that it is based only on one particular data set. We are aware of that. However, there are no data sets to our knowledge which are actually annotated with BMI information, right? So to further advance the state of the art, I think the path forward would be we have more data set with BMI annotated information, along with not only facial information, there should be multi-model data set. It should have other attributes for BMI prediction or weight monitoring. Thank you. If you have any questions, please let me know.
Question in audience? Any questions online? I don't think so. We have any questions. Let us thank the speaker. Okay.
Thank you.
Thank you. So then,
yeah, our next paper presenters, they are actually in India. Right now it's midnight, so they won't be able to present, but they did share a video presentation.
My name is Sumit Shekhar. I'm part of Adobe Research, and I'll be presenting our work on opaque, an optimized policy-based active learning framework for document content analysis. Our work focuses on the problem of document annotation with fixed budget and how to achieve maximum efficiency in labeling in this scenario. By document annotation, we mean the figure on the right, where we have a page, for example, the scientific article, and the user wants to annotate the structures on this page, for example, the abstract box, the paragraph box, title boxes, or the logos. And this is an important problem for document content analysis, where we want to examine the structures on the document page. However, there is a dense task where for each page, the user needs to draw multiple boxes and annotate it with the corresponding label, and hence it's quite time consuming. What we've done in this work is to develop an optimized policy-based method for annotating these document pages within a certain budget while maximizing the performance of tasks like layout detection or structure detection in these pages. We present opaque, a policy-based active learning framework for content detection in documents, where we have an annotator which is supposed to label documents with these structures, and we have a pre-trained prediction model. For example, we may have a faster RCNN model trained on a previous document dataset, and we want to retrain on a different dataset. And we have a pool of unlabeled data, and then what we have is a query or acquisition function which selects unlabeled documents for labeling by the annotator. However, in the case of the complex task of detection, prior work which relies on heuristics such as entropy becomes hard to use because we have multiple entities on the same page, and heuristics like using sum of entropies or maximum of entropy across instances may not work, and further there might not be any optimization related to the task of the class or the detection task itself in such heuristics. So what we proposed is a policy-based active learning framework which essentially optimizes the selection of the samples based upon the task in hand for the model. So we start with a pool of unlabeled data and this pre-trained prediction model. Then we compute something called an MDP state, which is essentially the output of the current pre-trained model on various unlabeled samples. And then we do something called action set, which are the set of documents to be chosen for labeling. Further, in this case, we just assume a weak annotation where we don't assume that user is going to mark every box on the page. Rather, we assume that the user is only going to correct the boxes which are predicted wrongly by the classifier, and maybe only draw the box completely if the classifier misses out on the box on that particular detection. And once this weak annotation is done, we retrain the prediction model, and then we compute reward for the policy training based upon the performance and the class distribution and the human feedback, which we will describe in further slides. Then we do performance of the policy optimization, and then we repeat the cycle for this active learning till the model is trained and the annotation budget is exhausted. And at the end, we have a prediction model trained on new data, and we have a policy network which is being trained to select samples for this particular task. So here we describe our deep query network and the reward calculation framework. So as we mentioned before, we want to optimize the selection as per the task in hand. So we have a generic reward function which we call as RT, which is essentially the change in performance before and after selection on a small held out set, which called as validation set. And for example, the performance metric we use, for example, for detection tasks, can use average precision or F1 score as metric for performance. And on the right, we have the description of the block diagram of this query network, in which we take the state vectors and the action vectors. We pass in through convolution networks and take a product and then pass into some more fully connected networks to get at the final Q values, which are then maximized for selections for particular action set using this reward. Further, to make the reward more general, we incorporate two novel rewards. The first is human feedback, where we essentially compute the delta performance before and after the feedback over the newly acquired set. The intuition behind this is if the user feedback is correcting the classifier performance, the performance of the classifier to start with must have been lower, and hence the user feedback adds value and corrects the classifier output. And secondly, for there might be class imbalance in the selection by the policy, where the majority classes or the classes with more samples get more selected. Hence, to overcome this imbalance, we have this entropy distribution over the newly labeled samples as a metric to overcome the class imbalance, and that we add to the initial reward function. So, training the policy, we need a small set of labeled documents to start with to essentially pre-train the prediction model. And then we have a randomly initialized deep query network. And the policy training happens as follows: like we have the cycle, as we mentioned before, and then this whole episode of RL gets repeated with all the cycles, where the policy gets optimized over different episodes. And while testing or deploying the policy, we start with this. We have again like this test set and the pool of unlabeled data, which needs to be annotated for the task, and then we have a trained deep query network, which we'll be using to select these samples for annotation. And this is the active learning cycle when the policy is deployed, where we just use the policy, the trained policy, to essentially select and get the model trained. And then in this case, we use something called 100% exploitation, where the policy is just the policy prediction is just used as it is to select the samples. We don't add random noise to as per in the training case, and there's no further policy optimization in the testing and deployment of the policy. And we essentially test our algorithm on two datasets: Pascal VOC, which is a standard object detection benchmark, and GROW2AP2, which is a large document dataset with annotations relevant to scientific articles. And we conduct experimental results and present our comparisons with entropy and margin sampling and random. And in this case, we can see it for object detection for VOC, the policy considerably outperforms the other random and entropy based sampling. For complete annotations, where we don't require the use, where we don't use the classifier output, and the user is supposed to annotate the whole image completely. And for weak labeling setting, again we see the policy of outperforming other benchmarks. Similarly, for layout, we see the policy outperforming other benchmarks over both complete and weak annotation labelings. So the key conclusions of our paper is we have proposed a novel RL-based active learning pipeline for document detection, content detection task. We have proposed human feedback as a novel reward, along with other rewards for better policy learning. And we have proposed a weak learning framework to further decrease annotation budget. The future directions, we would like to experiment with other objectives, for example, reducing the number of false positives and false negatives, trying out online learning of the policy to eliminate initial training of the policy, updating the deep query network with better networks, for example, active critique for policy optimization. And we would also like to experiment with something like transferring or deploying the policy to a completely new data set, for example, from VOC 2007 to 2012. Thanks a lot.
So next we have an invited talk. By Dr. Rahul Panikar.
Hi. All right. Let me.
Are you able to hear us?
Yeah, it's a little faint, but I think I can hear you now.
Come back to the microphone. So are you able to hear better now?
Yes, I'm able to hear better now. What about me? Are you able to hear me okay?
Yeah, it's pretty good. So I guess the last talk of the day is by Rahul Panikar, who is I guess quite well known in the community. He has several awards from MIT 35 and 35 and all kinds of awards that we have. Please look at his bio online, because I won't do it justice by trying to summarize in a couple of sentences. So he has done extensive work in South Asia, how AI can be used to improve quality of life. And so I guess he's going to talk about that, even though his current job is in a very different phase. And also, I guess he mentioned to us that it's also going to be, his company is being acquired by Meta, which is in public domain. So I guess it's
by Alphabet. Sorry.
Sorry, I mixed up the two. So thanks for correcting me. So I guess he's going to talk about today about his South Asian experience, I believe, right?
That is right. And I'll port some lessons over as
well. Okay, great. So I guess let's look forward. So I'm looking forward to personally to hear his talk. Thank you.
Great.
For joining. So go ahead.
And Nalini, when I have about 5 minutes left, if you could give me a heads up, that'll be helpful.
Yeah. So I guess we will certainly tap you on the messaging channel.
Sounds good. Yeah.
Okay.
Great. So hi everyone. So I thought I'd share some lessons learned in my maybe over a decade of working in using technology for social good. So I got my PhD at Stanford in electrical engineering, doing a lot of convex optimization and applying it to optical systems. But then after that, I would say the last decade or so, I've spent developing technological solutions for global development, largely based out of India, but scaled out to many countries in the developing world. And I'll share. And the last 5 years or so, I've done extensive work in AI for social good. And I'll share some lessons learned about what it means to do fair and trustworthy ML in that context. Some lessons learned, so that as we as a community develop general principles in the space, we keep other parts of the world in mind as well in developing these frameworks. So with that, the picture you see here is a low birth weight baby. There's about 20 million such babies born world over every year. And the way to weigh them is healthcare workers are sent out there to weigh them in a spring balance like this. Now, the global health world has been trying to do this for, I don't know, the past 15, 20 years. We still miss about half the babies born out there. half the low birth weight babies born out there are not weighed correctly, and if found, they are relatively easy to help. Right? And this is for a number of reasons. The reasons vary. It's sometimes supply chain of these spring balances never reach the villages where they needed them. They sit in storage facilities in state capitals. There are cultural taboos often where outsiders are not allowed to touch a newborn baby in the first 30 or 40 days of life. And for valid reasons, who knows how many babies have been in that sling before this baby is being put in there, right? And there's also data quality issues. This is something, this is a picture of a register I captured out in Rajasthan. The highlighted column shows the birth weight. Magically, all the babies born that year in that village weigh precisely 2.5 kilograms. I don't know how many of you are parents or have any background in neonatology, but 2.5 is a special number because that's the threshold for low birth weight. Below 2.5 is low birth weight, above that is normal. And somehow all these babies are precisely 2.5 at birth. You can imagine that there's some data quality issues here. So meanwhile, millions of healthcare workers have been given smartphones due to mHealth initiatives. Digital pipelines have been established. So we embarked on developing and this was when I was Chief Research and Innovation Officer at the Wadhwani Institute for Artificial Intelligence, a nonprofit AI research institute based in Mumbai. So this was work backed by the Bill and Melinda Gates Foundation. We headed out to develop an AI solution where basically the healthcare workers can take a short video of the baby, so no contact. And from the video, we can estimate weight of the baby. And this is possible because turns out babies are fairly constant density. We're quite similar when we're born. And so because babies are fairly constant density, from images, if we can estimate volume, we can actually get a fairly decent estimate of weight. Here are some early results. You can see we, in fact, went on to also do a 3D reconstruction of the baby by learning a low-dimensional deformable model. This is joint work with Makran Tapaswi, Jigar Doshi, Anju Kanazawa, Michael Black, Alamelu, and a number of other collaborators. And we started off doing this as a classification problem for classifying very low birth weight and low birth weight, and of course, normal. And fairly decent performance here, enough to actually be meaningful in the community. And this is work we did in collaboration with the health ministry, local health ministries, public health systems, digital health pipelines, and so on. You'll also see the weight discrimination showing up in the reconstruction and so on. And it also works in more complex backgrounds. The earlier background you saw was in a hospital setting. This is a background in a more typical village home. And I have a lot of experience doing technology for global development. Before this, I developed medical devices for newborn babies, which a company called Embrace, and we developed incubators that can work without electricity for premature babies. This has gone on to help over 1 million babies in over 25 developing countries since we launched back in 2012, so over the last 10 years or so. And I've learned a lot of lessons in this process. A key thing to keep in mind is that AI solutions should work within a broader system. Right? So if you go back to that previous solution, AI is only one part of any product that you make there, an app that runs on the healthcare worker's phone and all the necessary backend that creates the necessary alerts in the system. That entirety of it forms the product. But a solution needs more than a product. You also need to now modify workflows of how people react to this information. Given this information, how does the work of a healthcare worker change? What does the primary healthcare center doctor do differently from before? What does a state health officer do differently, having this level of transparency in weight tracking for newborns, one of the most important health metrics that exists for newborns? And ultimately, any solution for it to have scaled impact should sit within a larger context of systems. In this case, this is the home-based newborn care program that many countries have implemented. Right? And so it is my recommendation that when we design AI systems for social good, we actively look across the stack in implementation to understand the various stakeholders and their considerations. It's not just the end user or end beneficiary. There's only one stakeholder in this whole process. There's a lot of stakeholders, including funders, right? And so that brings us to the question of trustworthy ML, right? So just take this example. And we say trustworthy. Trust from whom? Is this trust from the mother who has to decide whether she has to panic or not based on the result that this AI system is giving, which she doesn't even know is an AI system, right? But it's healthcare worker comes here, gives his assessment, and then she has to decide what action she has to take, how concerned she should be based on the results the system gives. The frontline healthcare worker whose reputation in the community, whose trust of the community has been earned over many, many years, and she's a member of the community, right? And so her credibility is on the line in using new technologies. The primary healthcare center doctor, what does it mean for him or her to trust results from this, right? Too many false positives means crying wolf. And go back to the state health system. Again, they have to make the choice of, is this something that they want to roll out within their state health programs? So trust in the system to them means something else. There are regulators in the process whose trust relies on performance. And then ultimately there's also funders, funders like governments, the Bill and Melinda Gates Foundation, and so on, who also have to write checks for making these things happen. And so these systems also require their trust, right? So the point I'm making is in systems that that are necessary for AI for social good in the developing world, in the global south, so to say, the ecosystem, the stakeholder ecosystem is complex, and trust means very, very different things for very different people. For a lot of us, trust means having confidence in performance, knowing how things work, right, and so on. But knowing how things work is not even the most important source of trust for many people in the chain I just mentioned. Right? So this is something I would encourage everyone here to take away. Right? Trust for many stakeholders means very different things, and it's important to actually probe that early on. Typically in academia, in fact, this is an overly simplified model, right? Which is there's data, there's a metric we want to optimize, and we want to build good models that do this. But in the real world, the data is also a variable, right? Data is not a given. It's typically the problem that's a given, and the desired impact is a given, and both the data and model are variables, and even the deployment channel tends to be a variable. Right? And this also is a simplified model, right? If you look at the full life cycle of ML development, all these touch points involve making choices, right? And so my point being that this overly simplified model that most of us are exposed to in academia, okay, does not reflect reality, and the solution, the parameter space is much larger, right? And it's important to therefore not just pick the right problems, but also pick the right deployment models and what is the right data to collect. In the previous example, do we collect video? Do we collect images? What angles do we shoot this from? What lighting conditions, and so on? What is the set of babies that we need this data of, right? And we can talk more about this, but you can see that don't assume that the data is a given. In fact, data is a free variable, and as people who solving problems, we should engineer systems to collect the right data and establish the right deployment channels, right? Or work with the right deployment channels. The next point I'd make is the importance of evaluation. And you may have heard this in many quarters, but the recommended process for deploying systems where not all stakeholders understand the system is actually a four-step process. One is what we call lab safety, lab testing, which is basically what you do on a test set, right? It's primarily to assess safety, basic performance, and so on. And then you go to a controlled setting. So in the case of a medical solution, this would be a clinical trial in a hospital setting, right? Or it can even be in a community setting, but in controlled settings, right? And that's to measure efficacy. The first one is are we doing harm? The second one is, okay, we're not doing harm. Are we doing any good? The third step is an uncontrolled setting, because most real world use will be an uncontrolled setting. And that's where you test effectiveness. And that's, yeah, we're not doing harm. We're doing good in a controlled setting, but in the real world, will we do good? But ultimately, in the real world, things will get used in ways we cannot predict. And this is where the last point becomes important, that is post-deployment monitoring. And if I can leave you with one message of safely deploying these things, it's post-deployment monitoring. That is where a lot of systems fail, because designers anticipate certain test cases and test for it and then let it out in the real world. Things get used in ways and in conditions that are never anticipated, right? And bad things happen, right? And so post-deployment monitoring is possibly the most important step in the evaluation pipeline of any real-world AI solution. I'll skip over this. We've applied many of these principles into other solutions we will develop as well for smallholder farmers, in doing cotton farming. This has been successfully deployed in pilots, I should say, still in testing, but in pilots. And this is relatively uncontrolled setting. In 2,800 villages was deployed last year, and this year it led to a bumper crop yield. So there's great social impact possible if we wield the tools we have right. So with that, I'll go to the last part, which is, as Nalini mentioned, these days I do robotics. I am part of I'm part of Vicarious, which is a robotics company based in the Bay Area, and Vicarious recently got acquired by Intrinsic, which is a spin-off from X, part of Alphabet. The promise that robots hold is tremendous abundance, right? They hold the promise of dramatically dropping the price of many essentials. This is, some of you may have come across this. There has been a 10,000-fold decrease in the price of lighting, right? Just over the last 250 years or so in the world, right? And the benefit, and so many poor people can benefit from artificial lighting today, right? Same has happened with books, and robots hold the promise of providing a lot of abundance for much of our planet by dramatically reducing the cost of essentials. But here's, you have to ask the question, abundance for whom? Do we have systems in place to ensure equitable distribution of this abundance? And we just have to look at a recent example of, look at where COVID vaccines sit, right? This is the distribution, this is from a couple months ago, but it's the distribution of COVID vaccines by geography. It's just evidence that we haven't developed the systems to necessarily share in the abundance that our technologies can create. So if we talk about fair, trustworthy ML, right? The equitable distribution part is not something that we've solved, and it is important as technologists that we are cognizant of this and engineer systems deliberately towards this, because gone are those days when we could say that, oh, I'm just doing the technology, how it gets used is not my responsibility. No, as creators of the technology, we very much hold responsibility for the consequences of our creations, right? And with that, I leave you with two of my favorite quotes. This is by E.O. Wilson, right? That the real problem of humanity lies in the fact that we have Paleolithic emotions, medieval institutions, and godlike technology, right? And folks here have access to wielding this godlike technology, right? The real world is messy, but the real voyage of discovery consists, as Proust said, not in seeking new landscapes, but in having new eyes. And there are just fantastic possibilities that lie ahead of us if we wield our powers judiciously. With that, thank you. And if there are any questions, I'm happy to take them.
Thanks, Rahul, for coming at the end and giving us this insight. So are there any questions, comments for Rahul? Yes, come up to the microphone. So.
Thanks for the
Sorry, I'm having some trouble hearing you.
Maybe you come all the way here. That's the solution that we have.
Thanks for the great talk. So what you had these principles that you brought up, and you said the most important principle is to understand, is to be able to track the impact after once you're
Correct. Post-deployment monitoring. That's right.
Post-deployment monitoring. That's what you call it.
Yeah.
I wanted to get a better sense from you of how you mitigate issues that you find post-deployment, or how you even, monitoring is one part of it, doing something about it is the other side.
Of course, absolutely.
It's much harder.
Yeah.
It's much harder to do it, especially in the kinds of technology and the kinds of places that you're deploying this technology to. So I just wanted to hear your insights from that.
Right. So absolutely. So of course, the point of post-deployment monitoring is to be able to intervene if there are adverse situations detected, right? So there's a number of ways in which this can be done. And as the saying goes, what doesn't get measured doesn't get done, right? So to have any hope of intervention, we need measurement. Now, once we have post-deployment monitoring, the things we see need not be sort of stark, need not be binary. In some cases, there are, we find severe edge, we may find severe edge cases where the system is giving completely wrong answers, in which case, you actually try and build detection systems so that in those situations, you engineer the systems to say, I don't know. But sometimes it's more gradual. We'll find that in certain settings, the performance is degrading, right? It may be a graceful degradation, but there's still degradation of performance. And this is typically because of drift, right? And so in that case, it allows you to prioritize performance on those particular segments, right? So if it's the degradation of performance, then you sort of, for example, you may change your thresholds to play safer, right? Or you may actually focus a particular data collection effort for those settings in which this performance seems to be degrading to actually boost that performance, while also making sure that performance in other sets don't decrease, right? And I think maybe this is something I should have said explicitly. Most people who do real world deployments don't use just one test set, right? It's a test suite. So there's multiple test sets that we work with, right? And there's some minimum performance that is typically expected of all these test sets. Some of them cannot be violated, right? Or if there are other segments on which test performance is degrading, then you actually have to change the claims of performance. But essentially to this is a connect to the ground, right? So deployment often happens through partnerships. And so systems have to be established. So for example, in this solution, systems have to exist within the healthcare system. In the case of newborn baby weighing, systems have to exist in the newborn care system to recognize that intervention may be needed. These are expendable systems. And thankfully, those systems exist in many countries because of, like I said, mHealth initiatives. There is data literacy, data management systems. There are folks who are in charge of data. There are security policies and so on. And so we do get to piggyback on that. There is awareness that digital systems have to be dealt with in a certain way, and if necessary, certain interventions are needed. Right? I'll pause there. Have I answered your question?
Yes, thank you. Yeah, he says yes from the audience. Sorry.
Great. Yeah, I had that. Thanks.
I will not make him run over here to say yes. Are there any more questions? All right. So thank you, Rahul, for